Hello there, and welcome to Science for Sleep, a place where scientific curiosity unwinds itself slowly enough for your thoughts to settle. Tonight our step into the quiet is centred around an idea that has puzzled scientists, startled imaginations, and pushed the limits of what we consider possible. We're exploring the singularity, that mysterious point where the laws we trust decide they can't go any farther. It's a bit like reaching a door in the universe that refuses to open, because the blueprint for the room behind it hasn't been written yet. But before we move into that landscape, I'd like to know something about you. Where are you listening from tonight, and what time is it in your corner of the world as you drift into this moment? I always find it interesting how many different points on Earth gather here at once. Someone is ending their day while someone else is just beginning theirs, yet both arrive at the same quiet stretch of space at the same time. If this gentle way of wandering through science gives you even a small sense of rest, I'd truly appreciate it if you liked the video or subscribed. It helps others find this calm little place when their minds need somewhere soft to land. Now as we begin, try to settle into a comfortable position. Let your shoulders drop a little, let your breath loosen, and allow your thoughts to slow to a steady drift. Because when we step toward the idea of singularities, we don't rush. We let the ideas unfold in the same way darkness settles at the end of a long day, gradually, quietly, without sharp turns or sudden jumps. The idea of a singularity may sound dramatic, and in many ways it is. It sits at the heart of black holes, at the beginning of the universe, and at the edge of our understanding. But for our purposes, imagine it simply as a place where the universe becomes too intense for familiar rules to apply. Not a violent place, not a frightening one. Just a region where numbers rise beyond limits, and equations refuse to describe what happens next. Scientists use the word singularity because they needed a placeholder, a way of saying, this is where our current understanding stops making sense. In a way, it's a symbol of intellectual honesty. When we can't explain something, we mark it, leave a notation, and return to it as knowledge deepens. But before reaching the heart of that idea, it helps to look at the path that leads us there. Singularities didn't become central to cosmic thinking until general relativity reshaped how we saw gravity. In that framework, gravity wasn't just a force pulling things together. It became a consequence of how mass and energy distort the geometry of space. When enough mass collapses into a small enough region, the curvature grows so sharp that it defies the normal flow of time, and that is where the discussion of singularities begins. But I won't run too far ahead. For now, imagine a surface stretched taut, one that bends gently around small weights, but folds more dramatically around heavier ones. Add more mass, compress matter further, and eventually the surface doesn't bend in a way that we can easily describe. It reaches a point of failure, a point where our math returns answers that push toward infinity. That is the region we're approaching tonight. The interesting thing about this idea is that it doesn't come from wild guesswork. It comes straight from the same equations that describe how planets orbit and how light bends around massive objects. The same equations that predicted black holes before anyone had evidence they existed. When those equations are pushed far enough, they deliver a result that almost feels like a confession. They tell us that under certain conditions, everything collapses into something so dense, so tightly packed, that the geometry of space becomes undefined. Not in a mystical sense, but in a strict mathematical sense. It's as if a calculator tries to divide by zero, and the screen flashes an error because it can't express what that result should be. Singularities are the universe's version of that error message, except the stakes are astronomical. Still, while the math predicts them, the way we visualize them is always simplified. You might imagine a single point, infinitely small, containing everything that once belonged to a massive star. But this picture, while helpful as a starting point, is almost certainly incomplete. It's the best we can do until the deeper structure of space is understood. Physicists believe that quantum mechanics should step in when things become too dense, too compressed, too extreme for classical physics. But quantum gravity remains a work in progress, a patchwork of theories seeking a consistent shape. So, when we talk about singularities, we talk about regions where our descriptions break down, not because there is nothing to describe, but because we don't yet have the right language or the right tools. As you relax into this idea, you might notice a sense of drifting, the way a thought moves slowly when you're tired but still curious. That's the pace we're keeping, no rush. When exploring something as puzzling as a singularity, the pace shouldn't be hurried. It's not a concept that yields easily to quick explanations. It requires a kind of steady attention, the sort that notices details without gripping them too tightly. I've always found that ideas like this feel less intimidating when approached gently. Even the word singularity becomes less imposing when we remember that it's simply a placeholder for something we haven't yet understood. If you picture a star collapsing under its own weight, squeezing tighter as nuclear reactions shut down, you begin to see where singularities enter the picture. The star's core falls inward, the pressure rising, the density climbing, the temperature escalating to unimaginable levels. Eventually the collapse becomes unstoppable, and nothing can counterbalance the inward pull. In classical general relativity, this collapse doesn't stop until everything is compressed into a point. But that's where classical physics becomes uncertain. A point of infinite density is not a physical object. It is a sign that the equation has been pushed beyond its valid domain. Much like using a simple map to navigate terrain it was never drawn for, the instructions no longer match the landscape. That mismatch is at the centre of the singularity problem. You may notice that as we move through these ideas, the pace remains steady, each thought settling before the next begins. That kind of pacing mirrors how scientists often think about these concepts. They don't race toward answers. They sit with the uncertainty, patient but persistent. And that patience is part of why singularities remain so fascinating. They mark places where deeper theories are necessary, where the next steps in physics must be taken. They force researchers to refine, to reconsider, to revise. Some people imagine singularities as catastrophic locations, places where reality tears or collapses. But from a scientific standpoint, they are better thought of as unfinished descriptions. When a star collapses, something happens at the centre, but we currently lack a theory that accurately describes the conditions there. Whether it's a point, a loop, a region, or a structure we don't yet have a name for, the important thing is that reality continues past where our equations give up. The story doesn't end because our knowledge stops. That's an encouraging fact. It reminds us that the universe doesn't depend on our understanding in order to function. It simply does what it does, steadily, consistently, while we work to keep improving our models. You may be getting comfortable with the idea now, adjusting to the notion that singularities are less about final answers and more about boundaries in our current understanding. As you settle into that, let your thoughts drift slightly, the way they do when you're listening to someone speak softly about something intricate. You don't need to grasp every detail yet. You don't need to remember every phrase. You simply need to let the ideas sink in slowly, like settling leaves in still water. You're not studying, you're not analysing, you're just listening, letting the picture form piece by piece. One of the most interesting parts of thinking about singularities is the realisation that they may not exist in the way early interpretation suggested. Many physicists suspect that when quantum effects are fully accounted for, the singularity will dissolve into something finite, something structured, something describable. It won't be an impossible point. It will be a region of extreme physics that we don't yet understand. Something dense, something dynamic, something governed by a set of principles waiting to be discovered. Singularities may be less like walls and more like locked doors. The door exists. The hinges are real, but we haven't found the key yet. If you're still relaxed, still breathing steadily, you're doing exactly what this journey calls for. The goal isn't to rush to conclusions, it's to let curiosity be calm enough to follow the thoughts without demanding immediate answers. When approaching singularities, patience is especially useful. Even the brightest minds in physics have spent decades contemplating them, refining interpretations, adjusting theories, and welcoming new insights. The progress comes slowly, the breakthroughs often taking years to solidify. And that slow, methodical process reflects the pace we're keeping here. As we continue this journey, we'll move deeper into what a singularity signifies in physics, how it forms, why horizons matter, why equations reach their limits, and how ideas like quantum gravity seek to fill the gaps. We'll explore different interpretations, from gravitational collapse to the universe's possible beginning. Each step will follow naturally from the last, just as tonight's ideas follow from the opening ones. And while the ideas may grow more intricate, the pacing will remain measured, unhurried, steady enough to give your mind space to relax. For now, let the idea settle that the singularity is not a destination, it's an indication. It points to something we haven't fully uncovered yet. It's a reminder that the universe still holds mysteries large enough to challenge every tool we currently have. And that sense of unfinished understanding is part of what makes the topic worth exploring. As you stay here with the quiet, in your own time zone, in your own room, the idea becomes easier to sit with. When people hear the word singularity, they often picture something dramatic, maybe even overwhelming, as if it were a spot in the universe set aside for impossible events. The truth is quieter. It's not a spectacle. It's a moment in our understanding where the rules we rely on stop giving reliable answers. Instead of offering a clear description of what happens, the mathematics begins to stretch, numbers climbing without bound until they lose meaning. That is the landscape we're entering now, a region where familiar ideas no longer hold their shape, and where the limits of theory begin to show themselves. It isn't a place of chaos, it's simply the point where our explanations reach their edge. To reach that point, imagine how scientists describe gravity using general relativity. The theory explains how mass and energy bend the geometry of space, and how objects move along the curves created by that bending. This framework works remarkably well. It has predicted countless phenomena, from the orbit of planets to the bending of light around stars. But under certain conditions, particularly when matter becomes extremely dense, the equations start behaving in unexpected ways. They continue to operate according to their instructions, yet the results they output push toward infinity, signaling that something deeper must be at play. That signal is what we call a singularity. This isn't the same kind of limit people run into during everyday experiences. It's not a situation where a device breaks or a tool stops functioning. It's more like a signpost in the mathematics itself. The equations remain intact, but the answers they produce stop being physically meaningful. When density grows too high, or curvature becomes too extreme, the numbers escalate without reaching a stable value, and that escalation tells us our description is incomplete. In other words, the mathematics is warning us that we've pushed a classical theory beyond its intended range. You can imagine the situation in a simple way by thinking about older tools used to describe the world before technology improved. Early maps might have shown coastlines as rough outlines, missing large stretches of detail. They worked well enough for general navigation, but if someone tried to use them for precise measurements, the gaps would become obvious. A singularity is like stumbling across one of those gaps. The terrain continues, but the map does not. The world doesn't end at that point, only the description ends. And when the description ends, curiosity takes over. The reason gravity brings us to this boundary becomes clearer when we look at gravitational collapse. When a star many times more massive than the Sun exhausts its fuel, it no longer has the outward pressure needed to counteract the inward pull of gravity. Nothing pushes back. The core begins to shrink, the surrounding layers fall inward, and the collapse accelerates. As the core becomes denser, the curvature of space grows stronger. Eventually the collapse becomes unstoppable. Nothing halts it, not even the tightest atomic forces. At that stage, the mathematics of general relativity predicts that the mass will compress to a point where curvature becomes infinite. This is the singularity predicted by classical theory, but the prediction doesn't come with a detailed description of what actually happens. General relativity wasn't built to describe the smallest scales of the universe. That's the domain of quantum mechanics, and because we don't yet have a complete theory that unites gravity with quantum principles, we can't describe what occurs in that environment with confidence. So while the classical equations point to a singularity, the physical reality inside such a region remains open. It might involve exotic forms of matter, modified spacetime structures, or entirely new behaviours that current theories cannot express. This is the first place where understanding falters. Not because scientists lack the ability to think about the problem, but because the mathematical tools needed to solve it don't yet exist in a fully consistent form. The singularity predicted by classical relativity is a placeholder. It tells us where our understanding collapses along with the matter. It marks the point where newer ideas are required, not because the universe becomes undefined, but because our equations do. As you settle into this idea, it may help to picture the process in terms of cause and effect. In the regions outside the collapsing star, everything behaves normally. Light moves along curved paths. Matter falls inward. Space-time stretches around the mass. But closer to the centre, as the collapse continues, the curvature grows more dramatic. It's similar to how a slope becomes steeper near a cliff. At some point, the slope becomes too steep to walk. At a singularity, the curve becomes too steep for conventional physics. Beyond that point, the usual mathematical instructions no longer apply. This doesn't mean that the centre of a black hole is empty or mystical. Quite the opposite. Something is there, and whatever occupies that region must follow laws of nature, even if we haven't discovered them yet. The singularity simply marks the point where our current laws reach an unfinished boundary. It reminds us that a complete theory must extend beyond classical physics, accounting for extreme density, extreme curvature, and extreme energy. Scientists believe that quantum gravity will eventually fill in these missing details. But until that theory is fully formed, the singularity remains a signpost rather than a complete description. The idea that relativity leads to a breakdown isn't a failure of the theory, it's a clue. The theory accurately describes large-scale behaviour, but it wasn't constructed to operate at the smaller scales. When matter collapses far enough, those small scales become essential. Quantum effects must take control. Without them, the equations produce infinities because they're trying to apply a large-scale framework to a realm where it doesn't belong. It's like trying to measure atoms with a yardstick. The tool remains accurate for its intended purpose. It simply wasn't built for that particular domain. This boundary becomes even more intriguing when we consider how general relativity usually handles intense curvature. For most astrophysical situations, curvature remains finite. Even near the surface of neutron stars where density is enormous, the equations behave normally. But as the collapse progresses beyond that limit, general relativity lacks a mechanism to resist the rising curvature. It predicts that curvature increases without stopping, leading to infinite values. In physical terms, infinite curvature doesn't make sense. It isn't a condition that can exist in the real universe. It's a sign that the classical model has reached its limit. If you think of this in terms of scientific progress, singularities serve as a kind of directional marker. They show where exploration must continue. Every major shift in scientific understanding began when existing theories could no longer account for new evidence. Quantum mechanics arose because classical mechanics couldn't explain atomic behaviour. Relativity arose because classical gravity couldn't describe high-speed motion or strong gravitational fields. Singularities stand at the threshold of another shift. They signal the next frontier in physics. The interesting part is that singularities aren't just theoretical constructs. The gravitational collapse that forms black holes is consistent with what we observe. We see objects orbiting in visible massive centres. We detect gravitational waves from merging black holes. We observe stars being pulled around regions of intense mass. These observations don't reveal the interior, but they confirm that the collapse predicted by relativity happens in nature. So the singularity isn't an abstract idea. It's the predicted core of something physically real. The question isn't whether gravitational collapse happens. The question is what the collapse ultimately leads to once quantum effects take over. This brings us to another point where understanding falters, but in a productive way. Classical equations predict the formation of an event horizon, the boundary beyond which nothing can escape. That horizon forms before the singularity appears. Once the horizon exists, information cannot escape outward. That means we can't observe what happens inside. But this limitation doesn't mean nothing happens. It simply means that whatever happens occurs beyond the reach of outside observers. For the person falling in, the experience would continue, at least for a time, until they approach the centre, and at the centre, classical relativity says the singularity awaits. Yet when researchers think deeply about this, it becomes clear that the singularity isn't just a mathematical curiosity, it's a sign that something profound is happening. It indicates that spacetime becomes so distorted that the structure of the theory itself collapses. To resolve this, scientists look toward quantum mechanics. In quantum theory, particles and fields behave differently from classical predictions. They have discrete properties, probabilistic behavior, and uncertainty built into their foundations. If spacetime itself has quantum properties, then those properties should become dominant near the center of a black hole. This idea leads to several possibilities. One possibility is that quantum pressure prevents complete collapse, forming a dense core rather than a mathematical point. Another possibility is that spacetime has a discrete structure, preventing infinite curvature. Some approaches propose that geometry becomes quantized, meaning spacetime cannot shrink beyond a minimum size. In that case, the singularity would be replaced by a region of high but finite density. Other theories suggest that collapse may bounce, creating a transition from one region of spacetime to another. These ideas remain speculative, but they illustrate the ways physicists attempt to replace the singularity with something physically meaningful. As you consider these possibilities, keep in mind that the point of failure in our equations doesn't imply failure in nature. The universe doesn't malfunction. It continues according to laws that may be beyond what we currently know. The singularity is a marker, not an endpoint. It tells us where the path forward lies, not where it stops. And while we currently lack the complete map, the clues within general relativity point us in the direction where new theories must be built. If you think about the history of science, this pattern appears again and again. Every theory has its domain of validity. Newton's laws describe motion at everyday speeds but break down at high velocities. Classical thermodynamics explains heat on large scales but fails at the atomic level. Each time a boundary appears, scientists extend the framework or create a new one. Singularities represent the next boundary. They remind us that gravity must be described in a way that includes quantum behavior. Until that theory exists, the singularity stands as the formal location of our incomplete understanding. As you settle into these thoughts, you may feel the idea becoming more familiar. Instead of imagining the singularity as a literal point, it becomes easier to see it as a placeholder for something still unknown. That unknown doesn't need to be intimidating. It's the same kind of unknown that has motivated centuries of discovery. The singularity is simply the next question waiting to be answered. And the point where understanding falters is also the point where curiosity grows strongest. With time, new tools will emerge, and the placeholder will be replaced with a clearer description. The idea that gravity could reach a point where it no longer behaves the way we expect might sound unusual at first, especially because gravity is one of the most familiar forces in daily life. It keeps your feet on the floor. It shapes the trajectory of a thrown ball. It holds the moon in its orbit. Its reliability feels automatic. Whenever you drop something, you know exactly what will happen. Gravity never surprises you in ordinary conditions. It pulls steadily, predictably, without any sense of hesitation. Yet when gravity acts on truly enormous scales or under extreme compression, its predictable nature begins to strain. The same set of rules that governs an apple falling from a tree begins to break down when a massive star collapses. And it's at that point, when gravity pushes beyond its usual boundaries, that something completely different begins to unfold. To understand why gravity reaches this extreme, it helps to look at what gravity actually is in the framework of general relativity. Instead of thinking of gravity as a force tugging on objects, Einstein described it as the curvature of space-time. Mass and energy create a kind of indentation in space-time, and objects move along paths shaped by that curvature. This idea works exceptionally well for almost everything we observe. But curvature is not limited. It doesn't stop increasing at a certain threshold. When enough mass gathers in a small enough region, the curvature increases further and further without a natural mechanism to resist it. This raises a question. Why doesn't anything push back? Why doesn't gravity have an upper limit that prevents this runaway curvature? Other forces have natural cut-offs. Nuclear forces prevent atoms from collapsing beyond a certain point. Electromagnetic repulsion stops electrons from crashing into nuclei. Quantum effects stabilize matter under conditions that would otherwise crush it. But gravity, as described by relativity, has no such counterbalance built in. The more mass you have and the more tightly it's packed, the stronger the curvature becomes. And the stronger the curvature becomes, the more aggressively it pulls matter inward. This feedback loop is usually harmless. In a typical star, radiation pressure counteracts gravity. In a white dwarf, electron degeneracy pressure does the same. In a neutron star, nuclear forces provide the resistance. But when matter crosses the threshold beyond which these pressures can no longer counteract gravity, the collapse accelerates instead of slowing. All opposing forces fail, and at that moment gravity moves into a realm where it no longer behaves as a familiar stabilizing influence. It becomes overwhelming. If you imagine observing this collapse from a distance, you wouldn't see the interior directly. Instead, you would see the outer layers fall inward, heating as they compress. Stellar material would rush toward the core. Light would struggle to escape. As the collapse continued, space itself around the forming object would warp more sharply. If the collapsing mass reached the required density, an event horizon would eventually form. Beyond that boundary, not even light could escape. From the outside, this is where the story appears to freeze. Nothing seems to cross the boundary. Signals fade. The collapse seems to slow. But this is an illusion created by the difference in how time passes near such extreme gravity. Inside, the collapse continues. Space-time caves inward. Nothing halts the inward trajectory. No pressure pushes back. No known force stabilizes the matter. Gravity, usually a gentle curvature, becomes a steep descent. The collapse doesn't spread outward. It tightens. It funnels matter toward the center, creating conditions so extreme that all classical descriptions cease to function. This is the point where gravity seems to forget its limits. Not because gravity changes, but because our description of space-time stops being valid. The mathematics continues to operate, but the results lose physical meaning. The equations tell us that curvature rises without bound. They tell us that density climbs toward infinity. But these statements aren't realistic. They are signals that the mathematics is being pushed beyond its domain. To understand why, consider that general relativity relies on a smooth space-time. It assumes that space-time can be divided infinitely, that curvature can rise continuously. But quantum mechanics suggests that the smallest scales of reality are not smooth. They are likely discrete, or at least governed by uncertainty. At extremely small distances, the smooth geometry assumed by relativity breaks down. As a result, the predictions of infinite curvature are an artifact of applying a classical theory where a quantum theory is needed. At this point, it becomes clear why the behavior of gravity appears to lose coherence. The theory being used to describe it no longer applies. When matter collapses to scales smaller than any classical model can handle, the theory should transition to a quantum description. But because that quantum description of gravity doesn't yet exist in complete form, the classical equations simply continue their pattern until they produce infinities. The infinities themselves are a kind of alarm bell. They indicate that the existing equations cannot continue. The most important aspect of this breakdown is that the universe itself does not break. The collapse still occurs, gravity still acts, matter still follows whatever rules govern that environment. It's the model that fails, not reality. That's why it's inaccurate to think of the singularity as a physical point of infinite density. It's more reasonable to think of it as the region where the classical description gives up. The collapse likely continues into a quantum-governed domain, and whatever exists there has structure, rules, and behaviour that remain undiscovered. When physicists analyse this breakdown more closely, they find that the specific point where gravity exceeds its limits depends on the internal conditions of the collapsing object. For a normal star, the density never approaches these limits. For a neutron star, the density is extreme, but stable under the right mass. But beyond a certain mass threshold, roughly 3 times that of the Sun, no known material can resist compression. No arrangement of matter can counteract the inward pull. Gravity has no opposing force. Collapse becomes unavoidable. This inevitability is one of the most unsettling and fascinating aspects of strong gravity. Even if the collapsing matter attempts to arrange itself into the most stable patterns possible, gravity continues to compress it. There is no stable configuration available. The collapse is not chaotic. It is precise. It follows the geometry of relativity exactly. Every piece of matter, every photon of trapped radiation, every point in the collapsing core moves along geodesics that point inward. Those paths do not allow escape or reversal. They lead directly to the region where curvature grows too strong for classical theory to handle. Understanding why this happens requires thinking about spacetime as a dynamic structure. In most situations, spacetime responds to mass in a balanced way. But when mass becomes concentrated, the structure responds more aggressively. The geometry narrows, it steepens, and once that steepening reaches a critical point, the geometry collapses inward faster than light can escape. This is why the event horizon forms. It isn't a physical barrier. It's a region where every possible path light could take leads inward rather than outward. The collapse of space-time creates that boundary. Inside that boundary, gravity is not simply strong, it is relentless. The paths defined by the geometry all converge toward the centre. There is no stable orbit, no stationary point. Everything moves inward, and as the collapse continues, the curvature becomes more extreme. But again, this is only within the model of classical relativity. The model predicts infinite curvature, but that prediction says more about the model than about the universe. Many physicists have pointed out that infinities in equations almost always signal the need for a deeper theory. In the past, when infinities appeared in classical electrodynamics, it indicated the need for quantum electrodynamics. When infinities arose in early nuclear models, they pointed toward better descriptions of particle interactions. In every case, infinities revealed the limits of the current framework. The same is believed to be true of gravity. The singularity is not an actual physical feature. It is a placeholder marking the transition from classical gravity to quantum gravity. The question becomes, what actually happens in that domain? Several possibilities have been proposed. Some theories suggest that space-time cannot shrink beyond a certain scale because its geometry becomes quantized. Others propose that matter transitions into an exotic state where quantum pressure counteracts collapse. Still others propose that the collapse might rebound, creating a new region of space-time or a different configuration that prevents infinite density. Each of these proposals attempts to replace the singularity with a physical process. All of them share one idea. Gravity does not truly forget its limits. It only appears to do so because the classical description lacks the mechanisms needed at extremely small scales. Once quantum effects are incorporated, gravity may behave in a more controlled way, preventing infinite curvature and infinite density. But because the quantum theory of gravity remains incomplete, the exact mechanism is unknown. This frontier in understanding reflects why singularities draw so much attention. They represent the point where gravity exceeds the capacity of current theory. At this threshold, gravity transitions from a smooth geometric description to something more intricate. Without a unified theory of quantum gravity, the details remain unclear. But the concept of the singularity reminds us that gravity cannot be fully understood without quantum principles. It's worth noting that the same breakdown appears not only in collapsing stars but also in the early universe. The classical model of the Big Bang also predicts a singularity at the beginning of time, where density and curvature rise without bound. But just like in black holes, those predictions likely indicate that classical theory is being applied too far. The universe probably never reached infinite density. Instead, it likely passed through a quantum gravitational phase that classical relativity cannot describe. In both cases, gravity is being stretched beyond its domain. This connection between black hole singularities and the beginning of the universe suggests that understanding one may illuminate the other. If gravity has a different behavior at extremely small scales, that behavior might resolve both singularities. This possibility motivates research into quantum gravity, string theory, loop quantum gravity, and other approaches. Each one aims to replace the classical singularity with a physically meaningful structure. But until one theory succeeds, the singularity remains the formal location where current knowledge ends. As you reflect on this, the idea becomes more grounded. Gravity isn't acting irrationally, it's not defying rules. It's following a model that lacks the detail needed in extreme environments. The point where gravity forgets its limits is not a failure in nature, it is a limitation in theory, and once a complete theory exists, gravity will likely show consistent behavior even in the most extreme conditions. For now, the best way to interpret this region is as a reminder that our understanding is a work in progress. The universe doesn't adjust its behavior to match our expectations. It follows its own rules, and our theories gradually uncover them. The singularity is simply the location where our current tools fall short, and as those tools improve, that location will become clearer. When people talk about the collapse of massive stars, the conversation often focuses on the dramatic ending rather than the long and gradual process that leads to it. The truth is that a star doesn't rush toward its final state. It spends the vast majority of its life in an orderly balance, sustaining itself through reactions at its core that steadily convert lighter elements into heavier ones. The outward pressure from these reactions counters the constant inward pull of gravity. For millions or even billions of years, this balance holds firm. The star maintains a stable shape, shining quietly or brightly depending on its mass. Nothing about its day-to-day behavior hints that it will one day reach a point where no known force can stop its collapse. To understand how a star begins this journey towards something that pushes against the limits of physics, it helps to start with the basics of what a star is. A star is a sphere of plasma held together by gravity. In the core, temperatures and pressures are high enough to force hydrogen atoms to fuse into helium. This fusion releases energy. The outward flow of that energy keeps the star from collapsing. As long as hydrogen remains plentiful in the core, the balance remains stable, but the supply eventually declines. When the core's hydrogen is exhausted, the star must find a new way to support itself. For smaller stars, this transition takes them into phases where they expand, shed layers, and end their lives quietly. Massive stars follow a different path. Their cores contract and heat until helium begins to fuse. When helium runs out, the star continues climbing the ladder of elements, fusing heavier and heavier materials in a nested sequence of burning shells. Eventually it reaches iron. This is where progress stops. Iron consumes energy rather than producing it. There is no further step that provides outward pressure. Once a massive star builds up a core of iron, the balance that has held for so long begins to slide away. The collapse that follows occurs quickly compared to the long life of the star. The core, no longer supported by fusion, begins to contract under its own weight. As it shrinks, the pressure grows. The material becomes so dense that electrons are forced into protons, creating neutrons. This transformation is violent. It releases neutrinos and triggers a massive shockwave. In some cases, this shockwave tears the star apart, producing a supernova. What remains at the centre is incredibly dense. If the mass of the remaining core is small enough, neutron degeneracy pressure halts further collapse. This creates a neutron star, a stable but extremely dense object. However, if the core exceeds a certain mass threshold, even neutron pressure cannot resist the inward pull of gravity. At that moment, no known force can stop the collapse. The object passes a critical point, and the contraction accelerates. This is when the formation of a black hole becomes inevitable. The collapse continues without resistance. Gravity intensifies. Space-time curves sharply. The density rises far beyond the range of any everyday experience. From an external perspective, this collapse doesn't look as chaotic as one might imagine. The outer layers of the star may explode outward if a supernova occurs, but the central region continues shrinking in a controlled, steady progression. The material doesn't swirl wildly. It moves inward along paths defined by the geometry of the collapsing space-time. These paths, or geodesics, guide matter toward the centre with precision. There is no turbulence capable of undoing the collapse. Gravity dominates everything. As the core passes the critical radius associated with the event horizon, something fundamental changes for an outside observer. Light that once escaped now becomes trapped. From the outside, the collapse appears to slow. Time near the boundary stretches. Signals grow faint. The star's surface seems to freeze at the brink. But this perspective is not shared by the collapsing material. For anything falling inward, the journey continues. Time flows normally. There is no pause at the event horizon. The collapse simply proceeds. Inside, matter continues to compress. The geometry of space-time grows tighter. The curvature increases. The density rises. Based on classical general relativity, this process leads to a central point where curvature becomes infinite. But as we've already discussed, infinities in physics rarely indicate an actual physical condition. They are signs of a model being stretched beyond its useful range. Even so, the classical path remains informative because it shows how gravity behaves when nothing counteracts it. Without outward pressure, without supporting forces, gravity acts without limits. Every inward path points toward the centre. No stable radius exists. The collapse doesn't slow. It continues because the equations that govern the structure of the star allow no alternative outcome. Matter moves toward a region where our understanding falters. The journey continues beyond the point where classical physics provides answers. This process is often described as inevitable, but it's more accurate to say that it follows directly from the equations governing space-time. Einstein's field equations link curvature to energy and momentum. When matter collapses to a sufficiently dense state, the curvature becomes steep. If the mass exceeds the threshold for any known counterforce, the field equations predict that the collapse cannot be halted. This isn't speculation. It follows from the same mathematics that explains planetary orbits and gravitational waves. The fascinating part is that the collapse is smooth from the viewpoint of relativity. There is no sudden shift or abrupt transition. The curvature increases gradually. The density rises steadily. The event horizon forms naturally when light paths can no longer find routes that escape. There is no physical surface at that boundary. It is a property of the geometry. Everything inside continues inward. Everything outside remains forever unable to witness the final stages. Once inside, the collapse continues until classical theory hits its limits. The density grows toward values that cannot be represented meaningfully. The curvature becomes too extreme. The proper description of space-time requires quantum mechanics. But quantum theory in its current form does not include gravity in a unified way. As a result, the collapse leads to a region where our tools stop working. That region is identified mathematically as the singularity. The collapse itself, however, does not end at the singularity. It is simply the point where the mathematics indicates an unresolved frontier. The physical process that follows remains unknown, but what leads up to that point is well understood. The star collapses because gravity overwhelms every opposing force. The equations demand that the collapse continues. No configuration of known matter can resist. To get a sense of why this collapse becomes unstoppable, consider the behavior of dense matter. Electrons cannot occupy the same state, and this creates electron degeneracy pressure. That pressure stabilizes white dwarfs. But when the core becomes more massive, electrons are forced into protons, forming neutrons and releasing neutrinos. The resulting neutron-rich matter resists compression, creating neutron degeneracy pressure. But even that pressure fails at high enough mass. Once the mass exceeds the upper limit for neutron stars, the collapse resumes. At that point, matter no longer behaves as individual particles. It becomes a continuous compressed mass. The structure is governed not by atoms, but by the geometric behavior of spacetime. Gravity takes complete control. The collapse is not explosive. It is calm, steady, and irresistible. The geometry funnels everything inward along a precise curvature. No irregularities, no disturbances, no instabilities are capable of stopping it. The collapse is governed entirely by gravity. This progression continues until the curvature becomes extreme. But extreme in this context means something more than a steep gravitational gradient. It means that distances, areas, and volumes lose their classical meaning. When geometry collapses inward so sharply that the mathematics cannot provide finite values, the theory has reached its limit. That is where the singularity appears. Before reaching that limit, however, the collapse passes through stages that can be described accurately. The curvature increases, the inward paths narrow, the time it takes for matter to travel to the centre shortens. The structure becomes layered in a geometric sense. The closer something is to the centre, the faster its collapse proceeds relative to nearby points. This layering is a feature of the geometry, not a physical stratification. One might wonder whether the collapse encounters any internal resistance. Classical relativity suggests it does not. There is no pressure at that point. No force pushes outward. The matter follows the curvature. It doesn't fight against it. The collapse isn't forced. It flows along the paths defined by gravity. This flow leads directly toward the centre. From the outside, none of this is visible. The event horizon isolates the interior. Information cannot escape. The collapse becomes a hidden process, but its consequences are detectable. The mass remains. The gravitational influence remains. The surrounding spacetime reflects the presence of an intense gravitational well. Black holes can merge, interact, and influence their surroundings. They are astrophysical objects with observable effects, but their interiors remain inaccessible. This raises an interesting question about what can be learned from the collapse if the interior is hidden. The answer lies in how gravity shapes the environment around the black hole. By studying the behavior of matter falling in, the motion of nearby stars, and the emission of gravitational waves, scientists infer the presence of deep collapse. The details inside remain unknown, but the collapse itself is confirmed by external observations. This makes the collapse of stars one of the few natural processes that reliably leads to a region where classical physics cannot fully describe what happens next. The most striking aspect of this process is how ordinary the beginning feels. A star reaches the end of its fuel. Gravity takes over. The collapse begins. Step by step, the outward forces fail. The collapse deepens. Only in the final stage does the behavior approach the unresolved domain. The process is continuous. There is no sudden leap. Gravity brings matter from stability to instability in a way that feels almost procedural. If the mass is high enough, the collapse cannot be stopped. If the mass is lower, a different stable object forms. The difference lies entirely in how gravity balances against pressure. The idea that such a familiar process, gravity acting on mass, can lead to an environment where space-time breaks down is one of the most compelling parts of astrophysics. It shows that limits in our understanding can be reached through natural, inevitable processes. The universe doesn't need extreme conditions that violate ordinary behaviour. A star simply follows its natural evolution until the collapse reaches a point where new physics must take over. This path from stability to collapse, from ordered fusion to unstoppable contraction, becomes the mechanism by which something extraordinary emerges. A region of space-time so curved that our theories cannot describe it, a boundary beyond which no information escapes, a core where density rises beyond meaning. The collapse of a massive star is the simplest and most direct route to that region. Nothing artificial or speculative is required. The universe performs the experiment continuously. Understanding the collapse helps clarify why singularities appear. The collapse doesn't fail, the mathematics does. And the collapse of stars reveals how gravity, when unchecked, pushes space-time geometry to a form that classical theory cannot handle. This is why the formation of black holes is not just a curiosity. It is the clearest indication that our understanding of gravity is incomplete. When people first hear the term event horizon, it can sound dramatic, almost like something taken from a story rather than a scientific framework. But the idea itself is straightforward once the steps leading up to it are clear. The collapse of very massive stars eventually produces a region where the curvature of space-time becomes so steep that there is no longer a path for light to escape outward. This boundary isn't a surface in the ordinary sense. You couldn't touch it or see it hovering in space. It doesn't reflect or block anything. Instead, it is defined entirely by the way geometry influences the movement of light and matter. It's the place where outward paths turn inward, not because something pushes them, but because the structure of space-time leaves them no alternative. That makes the event horizon one of the most unusual boundaries in nature. It's not a wall, yet nothing gets past it. It doesn't stop objects. Objects simply cannot travel outward once they reach it. The boundary looks ordinary to anything falling in. It doesn't shine or flicker or distort. It behaves more like an unnoticed threshold in a room you've walked through without realizing it. Only someone outside the room sees that it separates two regions. Inside, everything continues as before, at least for a while. Outside, information about what lies within becomes inaccessible. This disconnect between interior and exterior perspectives is one of the most striking aspects of horizons. For anyone observing from a safe distance, the collapse of a star toward this boundary appears to slow, as if time is stretching. Light from the falling matter becomes redder and dimmer. The outer material seems to approach the boundary endlessly without crossing it. But this appearance is not shared by the material doing the falling. To the collapsing matter, time does not stretch. The boundary is crossed without pause. There is no delay, no change in the flow of time, and no physical surface marking the transition. What appears frozen from outside is entirely continuous inside. This difference arises because time itself behaves differently near strong gravitational fields. The rate at which time passes depends on how curved space-time is. Near an event horizon, the curvature becomes so intense that time slows drastically. From the perspective of distant observers, the collapsing star seems to hover. But that is a product of light struggling to escape, not a real pause in the collapse. The collapse continues out of sight, hidden behind a boundary that light cannot cross. Once the horizon forms, the interior becomes isolated. Nothing from inside can communicate outwards. Any signals, any particles, any information carried by light has no outward path. This isn't because something absorbs the signals. It's because every route they could take leads inward. The geometry forces every possible direction forward in time to point toward the center. That is what makes the horizon a boundary. It's a region where the structure of space-time dictates that escape is impossible. For the outside universe, this boundary has a simple consequence. The details of what happens inside can no longer be observed, but that doesn't mean nothing happens there. The collapsing matter continues its journey, following the inward paths defined by the geometry. Its motion is smooth. It does not freeze or distort. It simply moves into a region where the external world cannot follow. The most interesting part of this boundary is how subtle it is. From the outside, one can describe its size, shape, and the mass of the object that created it. The horizon grows or contracts depending on how much matter falls in. It can merge with other horizons if two black holes collide. But none of these changes reveal the details inside. The horizon is not a window, it's a limit on what can be transmitted outward. The formation of the horizon is a natural consequence of the equations of relativity. Nothing sudden occurs in the mathematics. The geometry gradually curves until all outward paths turn inward. That's the moment the event horizon forms. It doesn't require special conditions or added physics. It follows directly from the collapse and from how curvature works. Many people imagine the horizon as something physically dangerous, but crossing it would not feel unusual to an object falling in. The gravitational gradient near some black holes is not sharp enough at the boundary to cause immediate harm. Only deeper inside, where the curvature steepens dramatically, does the environment become extreme. But the horizon itself is not a destructive threshold. Its significance comes entirely from how it affects what information can escape. This creates an interesting situation. The collapse inside the horizon continues normally from the viewpoint of the material involved. But the rest of the universe can no longer observe that progression. The boundary effectively removes that region from causal contact with the outside world. Anything crossing it becomes part of the hidden interior. The horizon grows slightly each time something enters, but the details of what the object experiences beyond that point are no longer shared with the outside universe. This raises questions about what it means for information or matter to be lost. In classical relativity, the region inside the horizon evolves according to the internal geometry. The information isn't destroyed, it's simply inaccessible from the outside. The horizon acts as a dividing line. On one side, signals can reach the broader universe. On the other, they cannot. This separation is purely geometric. To understand why horizons hide more than they reveal, it helps to look at how light behaves near them. Light normally spreads outward in many directions. Near a horizon, however, the curvature bends the paths of light inward. Even light emitted outward at an angle eventually bends back. At the exact boundary, light emitted outward stays on the boundary without moving away. Any slight inward push sends it deeper. Any slight outward push is impossible because the geometry does not permit that direction. The horizon is defined by this exact point where outward travel becomes impossible. Even though nothing can escape from inside, matter and light can cross into the interior easily. They follow geodesics that naturally lead there. This one-way behavior is what gives the horizon its defining property. It selectively blocks outward travel while allowing inward travel entirely. Because of this one-way nature, the horizon becomes the final barrier separating the outside universe from the region where classical theory predicts a singularity. This isolation gives rise to several important consequences. First, anything occurring beyond the horizon becomes unobservable. The collapse may continue, matter may compress, and space-time may reach conditions where new physics is required. But no signals return from that environment. This makes it impossible to test what the interior actually becomes. The region becomes a natural laboratory whose inner workings are permanently sealed. Second, the horizon erases direct evidence of the original matter's arrangement. The mass, charge, and angular momentum of the collapsing star shape the exterior geometry. But the fine details, how the matter was distributed, what elements it contained, whether it was rotating uniformly or unevenly, do not affect the external field once the collapse goes past the horizon. This feature is often summarized by the idea that black holes have only a few observable properties. But this is not because the interior becomes simple, it's because the horizon hides the complexity. Third, The horizon creates a gap between what we can describe and what we can observe. The equations describe the interior evolution based on relativity. But because no measurements can be made inside, those descriptions remain theoretical. They are based on how relativity behaves in ordinary conditions and extrapolated to extreme conditions. Without observational access, the theory cannot be confirmed or rejected in that region. This limitation is not due to technological constraints. It is fundamental to the geometry. This division between inside and outside becomes a central part of understanding black holes. The horizon is not the core of the mystery. It is the boundary marking where the mystery begins. Everything outside the horizon behaves according to well-tested physics. Everything inside depends on how gravity and quantum mechanics interact in extreme environments. And because the horizon seals the interior, it becomes impossible to study the singularity directly. This barrier also plays a role in how we define black holes mathematically. A black hole is not defined by the singularity. It is defined by the presence of an event horizon. The horizon determines which regions of spacetime cannot send signals to infinity. This definition does not require knowing what happens at the centre. It only requires knowing where the boundary lies. The interior may contain a singularity or something else entirely. But as long as the horizon blocks all outgoing paths, the object is considered a black hole. The simplicity of the horizon's external appearance contrasts sharply with the complexity it hides. Outside, a black hole can be described with a few parameters. Inside, the structure may involve unknown physics. This creates a situation where the most extreme processes in the universe occur behind a boundary that prevents us from observing them. The horizon conceals the place where theory runs out. It hides the region where quantum gravity is expected to emerge. It shields the part of space-time where the collapse crosses into domains that cannot be represented with classical models. This makes horizons one of the most important tools for thinking about the limits of physics. They tell us where geometry becomes strong enough to isolate regions of space-time. They indicate where our understanding needs to be expanded. They provide a natural gateway between what can be measured and what can only be inferred. It's also worth noting that horizons are not exclusive to black holes formed from collapsing stars. Similar boundaries appear in other contexts. The expanding universe has a cosmic horizon. Accelerating observers experience horizons. The concept of a horizon arises whenever the structure of space-time limits which regions can exchange information. But in black holes, the horizon is unique, because it surrounds a region where the collapse continues toward conditions that classical physics cannot describe. As we look closer, the horizon becomes a kind of interface. On one side is the external universe where light can travel freely and signals propagate outward. On the other side is a region where all paths lead inward. The difference between the two depends entirely on the curvature of space-time. The boundary itself doesn't reflect or interact. It simply marks the shift in geometric behaviour. Once this boundary forms, the interior becomes permanently separated from the rest of the universe. That is why horizons hide more than they reveal. They isolate the very region where explanations become incomplete. They shield the part of the universe where matter reaches densities and curvatures that classical theory cannot handle. They conceal the point where understanding falters most deeply, and yet without horizons, those extreme regions would not be hidden. Without this boundary, the collapse would be observable until the moment classical theory broke down. The horizon is the mechanism that prevents that breakdown from becoming visible. This structure turns the interior into a domain where theories can be explored but not tested. It forces scientists to consider what new physics might look like, and it motivates the search for a quantum theory of gravity because such a theory would be the first to make sense of the region behind the horizon. The quietness of the horizon is matched only by the depth of the questions it raises. It doesn't announce itself. It doesn't glow or distort space in a way visible from afar. It simply marks the place where outward travel ends. It creates a boundary whose presence we infer through gravitational effects, rather than direct observation. Every property we measure from the outside tells us that the horizon exists, but none of those measurements reveal what lies beyond it. Trying to understand what happens near the centre of a black hole can feel like attempting to study a room when all the lights are off and every window is sealed. Instead of giving up, physicists turn to the one tool that keeps offering consistent guidance: the framework of general relativity. Even though relativity eventually reaches its limits in these environments, it still provides the clearest view available. It acts like a lantern that doesn't illuminate the entire space, but reveals enough structure to trace the outline of what lies ahead. Relativity begins with a simple idea that becomes more intricate the longer you follow it. Gravity is not a force in the traditional sense, but a manifestation of space-time curvature. Objects move along paths shaped by that curvature. They don't need to be pulled or pushed. They follow the geometry naturally. In familiar conditions, that curvature is mild. Planets orbit stars. Light bends slightly around massive bodies. Time passes at slightly different rates depending on altitude or velocity. These differences exist but rarely matter outside precise scientific measurements. Near a black hole, however, the curvature becomes much more pronounced. The lantern of relativity reveals how paths that once had many possible directions begin narrowing. It shows how the range of potential motions shrinks. Light that could once escape now struggles. The geometry starts funneling everything toward fewer outcomes. This progression is what guides physicists toward an understanding of extreme gravitational collapse long before quantum theory becomes necessary. One way relativity helps is by describing how space-time responds to increasingly concentrated mass. As matter collapses inward, the curvature sharpens. The lantern illuminates the gradient of this curvature, showing how it steepens as the collapse accelerates. The equations don't treat this region as chaotic. They describe it in an orderly way. The geometry becomes more constrained. The inward paths grow more focused. Nothing about this process is sudden. The lantern reveals a continuous narrowing of motion. This narrowing continues until the event horizon forms, marking the point where outward paths disappear. Relativity shows how the collapse continues behind that boundary without interruption. Even though an outside observer never sees matter cross the horizon, the internal view follows the inward journey clearly. Light, matter, and space-time all move along predictable paths. That predictability remains intact even though the outside universe can no longer observe the process. One of the key insights revealed by relativity is that space-time inside the horizon is not simply a deeper version of what exists outside. The geometry changes more dramatically. The inward direction becomes unavoidable. The concept of standing still no longer exists because the geometry doesn't allow it. Everything moves toward the center. This movement isn't caused by a force pulling objects inward. It is the result of how space-time is shaped. The lantern reveals that the center of the collapse acts not as a location that something draws matter toward, but as a geometric requirement. All possible paths lead there. As the collapse proceeds, relativity continues to describe how curvature increases. Time and space behave differently than they do in ordinary situations. Distances shrink more rapidly. Time intervals shorten. The lantern shows that the geometry becomes more distorted as the collapse deepens. But eventually the equations start giving answers that cannot be correct. When curvature approaches infinity, the theory is no longer describing a physical environment. It is overshooting its domain. This is the point where the lantern's beam fades. Relativity can describe everything leading up to this moment with clarity. It outlines how the collapse unfolds, how the horizon forms, and how the geometry evolves. But the final step, where curvature formally becomes infinite, is not something relativity can handle. The equations do not break physically, they break mathematically. They run into values that have no physical meaning. Even so, relativity provides a detailed picture of the approach to that limit. It shows how every possible path converges. It reveals how time behaves. It illustrates how matter compresses. It gives a coherent account of every stage except the last one. That makes the lantern metaphor appropriate. Relativity illuminates everything up to the doorway of the unknown. Beyond that doorway, another tool is required, one that doesn't exist in complete form yet. One of the strengths of relativity is that it doesn't rely on assumptions about matter's microscopic behavior. It treats space-time as a smooth continuum. This assumption works in many contexts, but becomes unreliable when matter reaches extremely high densities. The lantern shows the shape of the collapse, but doesn't show what matter becomes once quantum effects dominate. Even so, relativity gives an excellent approximation for everything up to that transition. This approximation allows physicists to trace the motion of collapsing matter. It describes how distances change, how time changes, and how the collapse interacts with the geometry. It shows that nothing stops the collapse. It shows that the singularity predicted is a sign of theory reaching its limit rather than a literal infinite point. That distinction is important because it prevents misunderstandings about what relativity claims. Relativity doesn't insist that the center of a black hole is a point of infinite density. It simply reports that, under its assumptions, the equations lead to infinite curvature. When a theory predicts infinities, that usually means the assumptions behind the theory no longer hold. Relativity assumes smooth space-time. When space-time becomes extremely compressed, that assumption may fail. But the lantern does its job well. It shows the point where the theory needs assistance. Before reaching that point, relativity gives a clear view of how horizons behave. It describes how horizons grow as new mass falls in. It explains how information becomes inaccessible behind them. It reveals how time dilation becomes extreme near them. These insights shape the way physicists think about black holes. The lantern doesn't reveal the interior in a direct sense, but it illuminates the structure that governs the interior's evolution. One of the most helpful contributions relativity makes is the understanding of geodesics, the paths objects follow when no forces act on them. In strong gravitational fields, these paths bend inward. Relativity shows how they bend, how rapidly they change direction, and how tightly they converge. This convergence is essential for understanding why the collapse cannot be stopped once it passes a certain threshold. Furthermore, relativity shows how different observers perceive the collapse. From far away, time near the horizon appears slowed, but for the collapsing matter, time flows normally. That difference is not an illusion. It is a consequence of space-time curvature. The lantern reveals that both perspectives are correct within their own frames of reference. This insight helps explain why observers outside see the collapse freeze, while the interior continues uninterrupted. Relativity also describes how tidal forces behave. These forces stretch objects along one direction and compress them along another. Near a small black hole, these tidal forces become intense near the horizon. Near a supermassive black hole, they can remain moderate until much deeper inside. The lantern helps distinguish these cases. It shows how curvature varies with mass. It explains why someone crossing the horizon of a supermassive black hole might not feel anything unusual at that moment, while crossing the horizon of a smaller black hole would be far more dramatic. The lantern also reveals how space-time structure becomes simpler in certain ways as curvature increases. For example, the interior of a non-rotating black hole becomes dominated by one direction, the direction toward the center. This dominance simplifies the behavior of geodesics. It makes the collapse extremely predictable. Everything moves inward regardless of initial motion. Even light follows paths that end at the center. This consistency helps physicists trace the evolution of the collapse even without knowing what happens at the final moment. Despite its successes, relativity's lantern shows its limits through its predictions. The theory predicts that space-time curvature becomes infinite at the center. It predicts that densities rise without bound. These results cannot describe a real physical environment. They indicate that the underlying model needs refinement. That is not a flaw, it is a useful signal. It tells physicists where the next step should be taken. This is why so much research is directed toward unifying relativity with quantum mechanics. Quantum theory describes particles, fields, and interactions at small scales. Relativity describes space-time at large scales. Near the centre of a collapsing star, both descriptions become relevant. The lantern of relativity illuminates the path until quantum mechanics becomes necessary. At that point, the lantern dims not because the path ends, but because another framework must take over. Despite this limitation, relativity remains essential for understanding black holes. It defines horizons. It describes their growth. It explains gravitational waves produced during mergers. It predicts how space-time warps under massive objects. Even without revealing the interior's ultimate structure, it guides nearly all the steps leading up to it. One valuable insight the lantern provides is that horizons are not the final mystery. They are simply markers. The true boundary lies deeper inside, where curvature becomes extreme. Relativity doesn't hide this. It makes the region's nature clear. It outlines the entire approach. It shows how close the singularity lies once the collapse begins. It describes the narrowing of the possible future trajectories for matter. In this sense, relativity does more than light the path. It shapes the path. It defines the geometry matter follows. It lays out conditions that predict the formation of horizons. It tells physicists what aspects of the collapse are unavoidable. Even though it eventually hands the problem off to quantum gravity, it brings us right to the doorstep. As you let these ideas settle, it's helpful to think of relativity not as a perfect description of everything, but as a consistent guide for the regions where it applies. It doesn't claim to describe the universe at every scale. It claims to describe space-time where curvature remains within its domain. Near a collapsing star, the lantern remains strong for most of the journey. Anyone examining the final stages of gravitational collapse eventually reaches a point where the usual methods stop giving reliable answers. Up to that point, general relativity works smoothly. It provides clear guidance about how space-time bends, how matter moves, how horizons form, and how collapse progresses. But the deeper one looks, the harder it becomes to ignore another framework that has been waiting quietly in the background. Quantum mechanics, normally content to describe atoms, electrons, and the smallest building blocks of matter, begins to intrude. It doesn't ask permission. It simply inserts itself because the physical conditions demand it. Quantum rules might seem far removed from collapsing stars, but density and curvature force the issue. As matter compresses, the distances between particles shrink. At a certain point, those distances become too small for classical descriptions to make sense. The particles are no longer arranged in any structure that can be treated as a smooth fluid. Their interactions become dominated by quantum effects. The radiation trapped in the collapse no longer behaves like classical light. The matter inside becomes so dense that the uncertainty inherent in quantum mechanics starts dictating how energy and momentum can be distributed. Nothing about these conditions resembles the environment relativity was built to describe. This confrontation between relativity and quantum mechanics is not dramatic in a cinematic way. It's more like watching two sets of instructions being applied to the same situation. Each works well in its own domain, but neither works well alone once conditions reach certain extremes. Relativity expects a continuous space-time with curvature that can increase indefinitely. Quantum mechanics expects discreteness, fluctuations, and limits imposed by uncertainty. These expectations clash when space-time shrinks to incredibly small scales. One of the first places this clash becomes obvious is in the prediction of infinite curvature. Relativity produces this result because it assumes space-time can be divided endlessly. Quantum mechanics, however, suggests that distances cannot be made arbitrarily small without altering what distance even means. At extremely tiny scales, fluctuations in energy become significant. These fluctuations distort space-time. Instead of a smooth continuum, space-time may behave more like a fluctuating environment, constantly shifting in ways relativity does not account for. This mismatch reveals that neither theory can remain silent. Relativity describes the broad outline of the collapse, but as the density rises, quantum mechanics steps in and begins altering the behavior of matter and energy. Those changes feed back into the curvature of spacetime, which relativity must then describe. But relativity does not include those quantum fluctuations in its equations. That exclusion makes its predictions unreliable near the end of the collapse. The idea that both theories must be considered simultaneously is straightforward in concept but extremely difficult in practice. Joining them requires a new framework, often referred to as quantum gravity. This framework must allow spacetime to behave in a way that incorporates quantum fluctuations while still respecting the curved geometry described by relativity. No complete version of this framework exists yet, but many attempts have been made to form one. Before discussing those attempts, it helps to understand why quantum mechanics must intervene. As matter is compressed during a collapse, the density grows so high that the wave-like nature of particles becomes important. Electrons, neutrons, and even quarks cannot be treated as tiny points following classical paths. Their positions become uncertain within extremely small regions, their energies fluctuate, their interactions reflect quantum rules, not classical expectations. These effects influence pressure, temperature, and structure, and those changes influence how the collapse proceeds. If relativity tries to describe these conditions without including quantum behavior, it ends up predicting infinities. That result is not a sign that nature becomes infinite. It is a sign that relativity is being asked to calculate something outside its proper domain. Quantum mechanics refuses to stay quiet because it must describe the physics of extremely small scales. It cannot allow relativity to ignore fluctuations that become dominant in these conditions. One of the clearest examples of this conflict arises when examining the last stages of collapse inside a black hole. Relativity claims that the collapse continues toward an infinitely small point. Quantum mechanics claims that matter cannot be confined to a zero-volume region with infinite precision. The uncertainty principle forbids such perfect localization. If matter were squeezed toward a point, its momentum uncertainty would grow without limit. That would generate enormous opposing pressures that relativity does not include. This is a direct contradiction. Both statements cannot be correct. This situation suggests that reality behaves differently from what relativity predicts. The singularity is likely avoided because quantum effects prevent collapse from reaching the infinite density state predicted by classical theory. Several models based on quantum principles propose alternatives. Some suggest that the collapse halts at a finite size. Others propose that the collapse rebounds. Still others suggest that space-time undergoes a transformation, creating a new region that classical theory cannot describe. In all of these possibilities, quantum mechanics plays a controlling role. However, these models differ in important ways. Some treat space-time as discrete. Others treat space-time as continuous but fundamentally fluctuating. Some propose new structures at extremely small scales. Others attempt to merge gravitational and quantum behavior through new symmetries. The variety of approaches reflects the fact that no single interpretation has yet been confirmed. The challenge remains open. Still, even without a complete theory, quantum mechanics provides hints about what should happen. It suggests that space-time cannot shrink indefinitely without reaching a scale where fluctuations dominate. This scale is often associated with the Planck length, an incredibly small distance where quantum gravitational effects become significant. At this scale, energy fluctuations are large enough to distort space-time substantially. Classical geometry breaks down. Smooth curvature is replaced by a more complex structure. This means that the classical prediction of a singularity is inaccurate. Instead of reaching infinite curvature, the collapse likely enters a phase where quantum gravitational behavior becomes central. The exact details of that behavior depend on the framework used. But all frameworks agree on one point. Infinities are replaced by finite, albeit extreme, values. Another way quantum mechanics disrupts classical predictions is through its treatment of vacuum energy. In classical physics, a vacuum is empty. In quantum physics, it is filled with fluctuations. These fluctuations generate energy and momentum that affect spacetime. Near extreme curvature, these fluctuations cannot be ignored. They alter the expected evolution, creating feedback that classical equations cannot incorporate. This feedback is important because it prevents spacetime from collapsing cleanly toward classical predictions. Fluctuations jostle spacetime. They modify the curvature. They introduce corrections that are magnified as the collapse deepens. This is why quantum rules refuse to remain silent. Once fluctuations become large, they take over. They push the predictions away from what relativity alone would suggest. Quantum mechanics also places limits on the compressibility of matter. Even when electrons are forced into protons to form neutrons, and neutrons are compressed to their limits, quantum rules create pressures that resist further collapse. These pressures do not stop collapse entirely if the mass is large enough, but they influence the path of the collapse. They shape the internal behavior. They introduce new terms into the equations, and in doing so, they ensure that classical predictions cannot remain accurate. This leads to the question of how to reconcile these conflicting frameworks. Many attempts have been made. String theory is one approach. It proposes that fundamental particles are not point-like, but are instead tiny vibrating structures. These structures have a minimum size which naturally avoids singularities. In this model, the collapse might create a compact region where strings are packed tightly. The structure could remain finite, preventing infinite curvature. Another approach is loop quantum gravity. It suggests that spacetime is made of discrete loops. These loops give spacetime a granular structure at extremely small scales. In this framework, the collapse cannot shrink spacetime beyond the size of these loops. Instead, the collapse might reach a minimum point and then transition to a new region. This could resemble a bounce or transformation. Other models propose that quantum corrections smooth out the curvature near the center. Instead of a singularity, the interior becomes a region with modified geometry. This region still lies beyond the horizon, but does not contain infinite values. It might be static, dynamic, or transitional. Despite their differences, these models share a common theme. They show that quantum mechanics cannot remain silent once densities and curvatures become extreme. They demonstrate that the classical prediction of a singularity is not a literal description of nature. It is an artifact of applying relativity without quantum corrections. It's important to recognize that these quantum models do not alter the existence of the horizon. They alter what happens after the horizon is crossed. The horizon remains a boundary for information. It remains a surface beyond which signals cannot escape. Quantum mechanics changes the interior, not the exterior. It replaces the singularity with a region governed by new rules, but it does not remove the horizon or the phenomenon of gravitational collapse. This separation between exterior and interior behavior underscores why quantum rules become relevant only in specific regions. The exterior remains dominated by classical curvature. The interior shifts into a domain where quantum fluctuations take over. That transition marks the place where current theory reaches its limits. While researchers continue exploring these ideas, the interplay between relativity and quantum mechanics remains one of the most important problems in modern physics. The two theories offer different insights, each essential in its own domain. But neither can describe the entire process alone. The collapse of matter behind a horizon forces them to interact. The fact that quantum mechanics refuses to stay quiet is not an inconvenience, it is a necessary feature. Without quantum rules, the collapse leads to contradictions. With quantum rules, the collapse leads to new possibilities. Understanding these possibilities will require deeper study, more detailed models, and perhaps entirely new mathematical tools. But for now, the path is clear. Quantum mechanics must have the final word in the regions where relativity's predictions fail. Most people assume that when a scientific theory produces an answer, that answer describes something real in the world. But every so often, a theory returns a result that doesn't describe anything at all. Instead of giving a number that can be measured or interpreted, it produces something that isn't physically possible. In mathematics, that often shows up as division by zero. In physics, the same kind of breakdown appears when an equation tries to model conditions it wasn't designed to handle. That is what happens when relativity is pushed deep into the core of a collapsed star. The final value it predicts isn't a measurement, it's a warning. It's the point where the equation breaks. This is why physicists refer to singularities as places where the mathematical description fails, not places where physics fails, not places where nature stops, just places where the mathematical tools stop giving meaningful answers. If someone using a calculator tried to divide a number by zero, the device wouldn't produce a long string of digits, it would flash an error. The calculator isn't revealing some hidden structure inside the number, it's telling you the operation doesn't make sense. Singularities serve the same purpose in relativity. They highlight the moment where the model is being forced past what it can reasonably describe. To understand why this matters, think back to how relativity handles gravity. The theory treats gravity as curvature in spacetime. When mass compresses, curvature increases. Under most circumstances, the equation describing curvature behaves exactly as expected. It produces values that correspond to the bending of light, the motion of planets, and the structure of galaxies. But when collapse becomes extreme, the curvature predicted by relativity begins to rise at a rate the theory cannot sustain. Eventually, the theory tries to assign an infinite value to that curvature, and because infinite curvature has no physical meaning, the result signals a breakdown in the description. That breakdown does not imply that spacetime literally becomes infinitely curved. Instead, it means that relativity has reached the limit of its applicability. The theory needs assistance from quantum mechanics at that point, but the required unified framework does not yet exist. This absence leaves the singularity as a placeholder. It marks the point where relativity stops working. In that sense, the singularity is the ultimate example of an equation running into a condition it cannot represent. This interpretation can be difficult to accept at first, because people often think of a singularity as something physical at the center of a black hole. But the singularity is not an object. It is not a point in space that someone could reach or observe. It is a mathematical signal embedded in the equations. It arises when the classical model encounters conditions it cannot describe. That makes it a conceptual boundary rather than a physical location. Nature continues beyond that boundary, only the model stops. Understanding this distinction is essential because it changes how one interprets what happens inside a black hole. If someone believes the singularity is a literal point of infinite density, they may imagine the collapse ending at that point. But if the singularity is instead understood as the failure of relativity to describe the final stage of collapse, then the collapse likely continues into a quantum-dominated regime rather than terminating. This interpretation aligns with modern expectations. Quantum physics should take over long before infinite values appear. Even so, the fact that relativity predicts a singularity is extremely valuable. It doesn't mean the singularity is real. It means the theory is being stretched. Every major breakthrough in physics began when a theory revealed gaps in its own applicability. Classical mechanics failed to describe atomic behavior, leading to quantum mechanics. The equations of electromagnetism struggled with high-speed motion, leading to special relativity. Newtonian gravity struggled under strong fields and fast motion, leading to general relativity. Each failure pointed toward the need for a new framework. Singularities play the same role today. They mark the place where gravity must be combined with quantum principles. To appreciate how strongly relativity insists on this breakdown, one can examine how curvature behaves near the end of collapse. The structure of spacetime becomes so compressed that the distances between points shrink dramatically. The curvature increases rapidly. The equations begin producing derivatives of curvature that grow faster than any physical process. Eventually, the values diverge. This divergence is not a comment on the universe, it is a comment on the model. The equations are signaling that they are no longer describing something meaningful. Physicists often refer to this divergence as geodesic incompleteness. A geodesic is the path an object or particle follows when no forces act on it. Under normal conditions, these paths can be traced indefinitely. But near a singularity, the paths end abruptly. Not because the universe ends, but because the equation defining them produces no continuation. This end of the path is the mathematical manifestation of the breakdown. It shows where the description stops. This type of breakdown has occurred before in physics. When early models of the atom tried to explain why electrons didn't collapse into the nucleus, the equations predicted that electrons should spiral inward. The predictions were wrong because the model was incomplete. Quantum rules were missing. When those rules were added, the model stopped predicting collapse and instead predicted stable orbits. The singularity in relativity plays the same role. It is a sign that additional rules, quantum gravitational rules, are needed to resolve the incomplete picture. The idea that singularities represent incomplete equations becomes clearer when one examines proposed alternatives. Several theoretical frameworks attempt to describe what happens in the regime where relativity fails. Some introduce quantum pressure that prevents complete collapse. Others propose that spacetime becomes discrete. Certain models suggest that the collapse transitions into a new region of spacetime. None of these ideas include infinite curvature. All of them eliminate the singularity by replacing classical assumptions with quantum corrections. This consistency across models is encouraging, because it suggests that infinite curvature is not a physical reality. It is instead the final output of a model that has reached the edge of its useful range. The singularity is the mathematical equivalent of a boundary marker, indicating where a different set of instructions is required. Even though the singularity is not physical, it remains crucial for understanding the structure of black holes. It indicates where the quantum description must begin. It shows the scale at which classical predictions become unreliable. It represents the location where the necessary corrections become so large that relativity no longer applies. Without this signal, scientists wouldn't know where to look for the next stage of theory. This interpretation leads to an important point. The singularity is not the centre of the black hole in a physical sense. It is the point where the mathematical model stops producing valid predictions. The interior of the black hole might contain something entirely different, such as a region of extreme but finite density. The collapse might slow or stop when quantum pressure becomes dominant. Space-time might undergo a transition or restructure itself. The singularity does not describe these possibilities. It simply marks where relativity's contribution ends. Consider what would happen if someone tried to extend relativity deeper into the collapse. The equations would consistently produce larger and larger values, eventually becoming meaningless. This is similar to trying to use Newtonian physics to describe speeds near the speed of light. The equations return numbers, but the results don't match reality. That mismatch signaled the need for a new theory. The same pattern holds here. Relativity must give way to a theory that includes quantum mechanics. Quantum mechanics, in turn, provides several reasons why infinite curvature cannot be real. For one, the uncertainty principle prevents particles from being compressed into an infinitely small region. If their positions are confined too precisely, their momentum becomes too uncertain. That momentum uncertainty generates a large quantum pressure that should counteract collapse. Relativity ignores that pressure because it has no mechanism to include it. Quantum gravity would include it. Furthermore, quantum fluctuations in the vacuum would become significant at extremely small scales. These fluctuations generate energy and momentum that modify spacetime. In classical relativity, vacuum energy plays a minimal role in collapse. In quantum gravity, it may play a major one. This too prevents the classical singularity. But while these insights provide hints, they do not eliminate the need for a complete quantum gravity theory. Until such a theory exists, singularities will remain in the equations. They will continue representing the place where relativity produces results with no physical meaning. Despite the uncertainty about what replaces the singularity, one thing is clear. The singularity is not the end of the collapse. It is the end of the classical description. Quantum mechanics must take over. The collapse likely continues into a different regime that relativity cannot describe. But because the horizon prevents observation of that region, no direct measurements can guide the construction of the new theory. This lack of observational access makes the singularity more challenging than earlier frontiers. When quantum mechanics was developed, experiments could be performed to measure atomic behavior. When relativity was developed, astronomers could test predictions against physical phenomena. But inside a black hole, direct observation is impossible. The horizon blocks all signals. That makes the singularity a uniquely difficult boundary, both scientifically and conceptually. Even so, the existence of singularities has shaped decades of research. They motivate attempts to unify relativity and quantum mechanics. They force physicists to confront the limits of classical descriptions. They highlight the need for new frameworks, and they remind us that scientific theories are tools, not complete descriptions of nature. When those tools stop working, nature does not stop. The tool simply needs improvement. In that sense, the singularity is the most honest part of relativity. It doesn't pretend to describe what it cannot. It marks the limit clearly. It does not claim that nature becomes infinite. It claims only that the model has reached a point where it cannot continue. Understanding the breakdown helps reframe the structure of black holes. The horizon marks the boundary where information stops escaping. The singularity marks the boundary where equations stop describing. The region between them is governed by physics that remains incomplete, and the collapse that leads to these boundaries is a natural, predictable process. The deeper one tries to follow the collapse of matter inside a black hole, the more the familiar structure of spacetime begins to lose its usual character. Nothing about this transition happens suddenly, but it becomes impossible to ignore once the collapse moves far enough beyond the region where curvature is moderate. At first, spacetime bends in ways that are extreme but still understandable. Distances shrink. Paths converge. Time flows unevenly. These shifts follow directly from the rules of relativity. But as the collapse continues, the geometry stops resembling anything that exists in ordinary circumstances. The normal separation between directions becomes distorted. The relationship between time and space begins to shift. And eventually, the mathematical structure that once described space-time so cleanly starts behaving in ways that signal something far more complicated is taking place. It helps to begin with what space-time ordinarily is supposed to do. Under normal conditions, space-time provides a stable framework where distances and intervals can be measured consistently. Time moves forward at predictable rates. Space stretches out in 3 dimensions. Curvature influences how objects move, but the underlying structure remains intact. That stability is what lets planets orbit stars without drifting unpredictably. It's what makes the speed of light the same in all directions. It's what allows distances to be meaningful and measurable. As gravitational collapse intensifies, space-time starts behaving differently. The most noticeable change occurs in how directions align. In everyday experience, you can move forward, backward, left, right, up, or down. These directions remain distinct. But inside a black hole, the geometry rearranges itself. The inward direction becomes dominant. All possible future paths tilt toward the center. Instead of being able to move freely in 3 spatial directions, matter becomes constrained. The geometry funnels everything inward. This shift happens smoothly at first but gains strength as the collapse deepens. Another change appears in the way time and space relate to one another. Under ordinary circumstances, time flows separately from the 3 dimensions of space. But in extreme gravitational fields, the distinction blurs. Time can become intertwined with the inward spatial direction. The geometry rearranges which dimension acts like time and which act like space. These changes follow the equations of relativity. but they push those equations to their limits. The farther the collapse goes, the more dramatic these rearrangements become. As spacetime is compressed, certain intervals that once behaved normally begin to contract. Distances that would take measurable time to cross shrink rapidly. Time intervals grow shorter. The geometry becomes increasingly steep. These changes do not arise from any external force. They emerge naturally from the structure of relativity. The collapse reshapes spacetime from within. When curvature becomes sufficiently intense, the relationships that define distances begin to break down. Spacetime stops behaving like a smooth, continuous fabric. Instead, the mathematical description begins producing values that make no physical sense. Areas shrink towards zero. Volumes collapse. Angles distort. Curves that should be smooth become impossible to follow. This is the stage where the geometry becomes so twisted and compressed that the usual tools can no longer represent it. Even before relativity's breakdown becomes obvious, the geometry inside the collapse shows structure unlike anything in normal environments. For example, tidal forces become incredibly strong. These forces stretch matter in one direction and compress it in another. At a distance from the black hole, these forces are modest, but deeper inside they intensify dramatically. They do not arise from friction or impact. They arise from the way nearby geodesics converge or diverge. These stretching and squeezing effects are consequences of curvature, not mechanical action. As the collapse progresses, these forces escalate. They reveal how the geometry is distorting. The stretching direction grows, the compressing direction tightens, the distribution of curvature becomes uneven. This uneven distribution is another sign that spacetime is no longer maintaining a simple structure. It is being deformed beyond anything familiar. Relativity describes these distortions precisely, but only up to a point. The mathematics shows how distances shrink and how curvature rises. It shows how geodesics converge by increasing amounts. But it also shows where the equations begin producing results that diverge. These divergences indicate that spacetime is being pushed toward conditions that require quantum corrections. In ordinary experiences, spacetime is stable enough that its distortions are minimal. Even around massive stars or dense clusters, spacetime bends, but not enough to tear or fold. Inside a black hole, the curvature is so extreme that the shape of spacetime ceases to behave predictably. Every direction becomes warped. Every interval becomes distorted. The geometry is stretched in ways that cannot be visualized easily. Visual models often try to represent this by drawing spacetime as a stretched sheet or a funnel. But these illustrations fail to capture the depth of distortion occurring in the collapse. Real spacetime doesn't bend on a two-dimensional surface. It changes shape in 4 dimensions. Directions that once existed separately begin merging. Time begins to behave like a spatial direction in some regions. The inward direction loses its usual meaning, and as curvature increases, the geometry becomes so distorted that the classical picture loses validity. A helpful way to understand the distortion is to think about how geodesics behave. In a simple gravitational field, geodesics bend but remain well defined. Near a black hole, geodesics begin to converge so sharply that their future paths collide mathematically. That convergence is what leads to the singularity in relativity. It is not that matter is being crushed by external forces. It is that the geometry leaves no room for the paths to continue in a smooth way. They intersect in a way that defies classical description. That intersection marks the collapse of spacetime's normal structure. This collapse of structure doesn't mean spacetime tears in a physical sense. Instead, it means the mathematical description becomes inconsistent. The coordinates fail. The curvature diverges. The metric, used to measure distances and times, becomes undefined. These changes show that the underlying principles of relativity cannot be extended indefinitely. The geometry is being distorted into a regime where quantum principles must take over. Quantum mechanics suggests that spacetime cannot be treated as continuous at extremely small scales. Instead, it may have discrete units, or undergo constant fluctuations. These fluctuations become important when space-time is compressed enough. They prevent the kind of infinite curvature predicted by relativity. But because no complete quantum gravity theory exists, the exact replacement for relativity's breakdown remains unknown. This means the torn and folded structure predicted by relativity may not correspond to a physical state. It represents how the classical equations behave when pushed past their limits. The actual behaviour of space-time at those scales might be more stable once quantum corrections are included. But because those corrections are not fully known, the classical prediction stands as a formal boundary. Even so, the classical model remains useful. It shows how the early stages of collapse proceed. It identifies the conditions under which curvature becomes extreme. It illustrates how horizons form. It reveals where quantum mechanics must begin to dominate. And it provides insight into the way space-time compresses as the collapse deepens. One of the most striking features predicted by relativity is how the interior region becomes dominated by a single direction of motion. In ordinary space-time, one can travel in many directions. Inside a black hole, all future paths point inward. Not metaphorically, not because something pulls inward. The shape of space-time itself directs everything toward the centre. That is part of what it means for space-time to be twisted or folded. It is not a literal folding. It is the rearrangement of allowable motion. Another aspect of this distortion is the relationship between time and space. In normal conditions, time and space maintain separate identities, but in strong curvature, the metric that defines these identities becomes distorted. The time component can shrink, spatial components can stretch. The geometry that distinguishes time from space becomes altered. This change is not philosophical, it is mathematical. The metric that defines intervals loses its usual form. This is another sign that classical descriptions are being pushed beyond their limits. When physicists talk about space-time being torn or twisted, they do not mean that it rips like a material. They mean that the mathematical rules governing its structure stop producing finite results. Distances become undefined. Paths terminate abruptly. Directions blur. These outcomes indicate that the classical model is no longer representing something physical. Over the years, various theoretical frameworks have attempted to describe what happens when space-time reaches this regime. Some propose that space-time becomes discrete. Others propose that space-time undergoes a transformation into a new configuration. Some suggest that a bounce occurs, sending matter into a new region of space-time. None of these proposals include the classical singularity. All of them avoid infinite curvature. But because no single proposal has been confirmed, the classical prediction remains the formal answer. Even though the details remain unresolved, physicists agree that the classical picture cannot be literal. Infinite curvature is not physical. Space-time cannot shrink to zero volume. Matter cannot be compressed indefinitely. The singularity shows where the classical description ends. What happens next must be described by quantum gravity. Understanding this transition is central to modern physics because it marks the exact point where our knowledge is incomplete. The geometry leading up to that point is understood. The behaviour past that point is unknown. But because horizons prevent observation of the interior, direct measurements cannot guide the construction of the new theory. That is why the problem remains open. Still, the ability of relativity to describe the approach to this extreme regime is remarkable. The lantern analogy from the previous section still applies here. Relativity illuminates most of the path. It reveals how space-time distorts, it shows how curvature intensifies, and it makes clear where the mathematics stops. The breakdown is not hidden. The theory announces it loudly by producing infinities. What remains is the realization that this folding and distortion of space-time is not a malfunction of nature, but a limitation of the model used to describe it. Looking at how space-time behaves as the collapse pushes deeper into extreme curvature reveals a landscape that barely resembles the structure people are familiar with. In ordinary settings, geometry behaves in a way that allows distances, angles, and directions to follow predictable rules. The three spatial dimensions remain independent. Time flows at a steady pace. Coordinates can be set up so that motion is easy to describe. But when collapse reaches the innermost regions of a black hole, these familiar geometric features stop acting the way they should. They don't disappear, but they twist into shapes that stretch the meaning of geometry. The rules remain mathematical, but the results are far from intuitive. To understand why the geometry becomes so unusual, it's useful to recall what geometry means in the context of relativity. In this framework, geometry is not a simple background grid. It is the structure that determines how objects move. It tells matter how to travel. It defines the paths of light. It dictates the shape of time. When this geometry becomes distorted by gravitational collapse, everything influenced by it becomes distorted as well. The geometry doesn't just sit there. It pushes, shapes, and directs motion. Near the horizon, the distortion is significant but manageable. Distances behave differently. Time slows relative to distant observers. Light bends in steep arcs, but the geometric rules remain coherent. The metric describing spacetime still produces finite values. The curves can still be followed. As the collapse continues, however, these features begin to deform so dramatically that the geometric rules produce structures that cannot be extended indefinitely. A good place to begin is with the notion of distance. Under ordinary conditions, distances measured between 2 points follow predictable rules. The metric that describes how these distances behave remains well defined. But inside a black hole, the geometry compresses so intensely that distances shrink in one direction and stretch in another. This doesn't refer to physical stretching or compression of objects. It refers to the mathematical structure of spacetime itself. For example, the radial direction becomes compressed. Distances that would normally be measurable become extremely short. Meanwhile, directions perpendicular to the radial direction behave differently, sometimes shrinking at slower rates or distorting in more complex ways. These changes follow from the curvature, not from any material force. The next feature to consider is how the notion of direction changes. In everyday experience, directions are separate. One can point toward north, south, east, west, up, or down. Inside a black hole, those options collapse. The geometry dictates that all possible future motion tilts inward. This isn't a matter of preference or force, it is a matter of geometry. The inward direction becomes aligned with the direction of time. This realignment forces everything, including light, to move inward. This change doesn't happen because something pulls toward the center. It happens because time itself acquires a spatial component, and the spatial component becomes part of the path that must be followed. The strange geometry becomes even more pronounced when examining how geodesics behave. Geodesics are the closest thing relativity has to straight lines. In flat spacetime, they are straight paths. In curved spacetime, they bend according to the geometry. Near the center of a black hole, geodesics converge so sharply that they terminate. This termination is not a physical collision. It is a mathematical endpoint. The curvature becomes so extreme that the equations describing the paths produce an end. This end signals the breakdown of the classical description. It means the geometry cannot be extended in the usual way. Relativity treats this breakdown as inevitable under certain conditions. It doesn't claim the universe ends at this point. It only claims the classical model cannot continue. The fact that geodesics terminate shows where the limitations lie. This termination is the clearest indication that the geometry becomes too extreme for the classical equations. When geodesics no longer extend, the geometry can no longer be represented. That's how relativity signals the presence of a singularity. One of the more surprising features of the geometry near this region is how angles behave. Under ordinary conditions, angles add up in predictable ways. A triangle on a flat surface has angles that sum to 180 degrees. On curved surfaces, the sum changes, but it always follows rules that relate to curvature. Near a singularity, the curvature becomes so intense that the geometric rules predict angle sums that diverge. They may shrink or grow without approaching a stable value. These results are another sign that the classical description is nearing its limit. Angles are not physical objects. They are mathematical constructs. When those constructs stop behaving normally, it means the geometry underneath is no longer representable with classical tools. Time also becomes distorted in unusual ways. Even in weaker gravitational fields, time behaves differently at different locations. Clocks in stronger gravitational fields tick more slowly. Inside a black hole, these differences become extreme. The time component of the metric shrinks dramatically. It can approach zero. In classical relativity, when the time component of the metric approaches zero, time loses its usual properties. This doesn't mean time stops. It means the definition of time changes. In certain coordinate systems, the role of time and space switch. This swap is a mathematical statement about how intervals behave. It shows the structure becoming so twisted that the distinction between time and space becomes blurred. As the collapse moves inward, tidal forces grow rapidly. These forces arise from the difference in gravitational pull between two nearby points. In normal conditions, tidal forces exist but are small. Near a black hole, they become significant. Deeper inside, they become extreme. They stretch objects in one direction while compressing them in another, but their importance lies less in physical stretching and more in what they say about geometry. They show how the curvature changes across small distances. When the curvature changes dramatically over small scales, it indicates the geometry is being distorted into shapes classical theory cannot maintain. The sharpest corners of the universe are not literal corners. They are regions where the geometry becomes so intensely curved that classical tools cannot describe them. These corners represent the boundary of our understanding. They highlight where space-time stops acting like a smooth manifold. At these corners, the metric becomes undefined. The curvature diverges. The underlying structure cannot be extended. Quantum mechanics suggests that these features cannot be literal. It implies that space-time should have limits on curvature, or should behave differently at small scales. But until a complete quantum gravity theory exists, the classical picture remains the official description. That picture includes these sharp corners. Relativity provides additional insight into how these corners form. The equations governing curvature relate the distribution of matter and energy to the geometry of space-time. As matter collapses, the distribution becomes more concentrated. The curvature increases. This process continues until the distribution becomes so dense that the equation predicts the geometry will diverge. The shape of space-time is not torn physically. It is torn mathematically. The equation stops producing meaningful results. This helps clarify why singularities appear in relativity. They arise because the theory assumes space-time is smooth and continuous. When conditions push that assumption too far, the structure breaks down. This breakdown shows itself in the form of distorted geometry. The geometry behaves well until a certain threshold. After that threshold, it becomes impossible to extend the structure without adding quantum rules. Even though the geometry becomes extreme, the classical model still reveals patterns. It shows that the shape becomes anisotropic. That means different directions behave differently. The inward direction collapses faster than the tangential directions. The geometry stretches and compresses unevenly. This uneven behavior is a natural consequence of the collapse. It arises from the way the gravitational field varies across different directions. These differences can be seen by examining the curvature tensor, which describes how space-time curves. In ordinary conditions, the curvature tensor has modest values. Near a singularity, the values grow dramatically. Some components grow faster than others. This unequal growth shows how the geometry becomes distorted. Some directions stretch, others compress. The distortion is not random. It follows the equations exactly, but the equations lead to divergence. When components grow without bound, the geometry loses coherence. Another way to see the distortion is through expanding and contracting volume elements. In relativity, one can examine how a small region of space-time changes shape. In normal regions, the volume remains finite. Inside a collapsing region, the volume shrinks. Near a singularity, the volume approaches zero. This result is another sign that the classical model cannot describe the region fully. It suggests that space-time is being pushed into a configuration where the classical notion of volume no longer applies. Relativity treats this collapse of volume as part of the solution. It does not question whether it is physical, it simply follows its instructions. But quantum mechanics challenges the idea that volume can collapse to zero. It suggests that space-time may have a minimum volume. If that is true, then the extreme geometry predicted by relativity would be replaced by a more stable structure at small scales. Various quantum gravity models attempt to replace the classical picture of these sharp corners with something finite. Some propose that space-time becomes discrete. Some argue that space-time forms loops or networks. Others claim that the collapse triggers a transition into a new region of space-time. All of these models avoid the classical singularity. None allow infinite curvature, but they differ on what happens instead. Because the horizon hides the interior, there is no way to observe these small-scale corrections directly. That is why the classical model remains widely used. It is not believed to be literal in the final stages, but it accurately describes everything leading up to the breakdown. The geometry can be traced until the divergence appears. That divergence marks where the model must stop. The strange geometry at the universe's sharpest corners is not a flaw. It is a feature that reveals the boundary of classical gravity. It shows where space-time stops behaving in ways that can be represented by a smooth metric. Questions about what lies beyond the breakdown point of classical gravity tend to arise naturally once someone accepts that relativity cannot provide a complete description of what happens at the core of a black hole. Up to this point, the path has followed a fairly consistent thread. Matter collapses, curvature increases, classical equations fail, and quantum mechanics must eventually take over. But the moment the classical framework signals its limits, a new question emerges almost automatically. What happens after the breakdown? Does the collapse terminate? Does matter remain trapped? Or does the unresolved region open into something new? Proposing possibilities should not be mistaken for speculation without structure. Each idea about what could replace the classical singularity arises from attempts to merge relativity with quantum mechanics. These attempts follow rules, constraints, and mathematical principles. They do not claim to know the final answer. They explore the consequences of combining two theories that must eventually work together. And many of these attempts share one interesting feature. None of them treat the singularity as the end of the story. Instead, they treat it as the place where the next phase of the story begins. One reason this shift occurs is that singularities, as predicted by relativity, are not physical. They represent points where equations produce infinite curvature. Infinite curvature is not something nature produces. It is something a theory produces when it is being asked to model conditions beyond its design. If the singularity were literal, then physics would allow a zero-volume region containing finite mass with no further evolution. That outcome would be inconsistent with the principles of quantum mechanics, which forbid perfect localization of particles. Quantum rules require limits on how small a region can be before uncertainty forces new behavior. This means the classical singularity cannot be the final configuration. Once this realization takes hold, it becomes necessary to ask what replaces the classical singularity. The most straightforward option is that the collapse halts at a finite size, forming a compact, stable region. Some theories propose this outcome. They suggest that quantum pressure or quantum geometry prevents complete collapse. But other models propose more dynamic outcomes that resemble transitions rather than terminations. Before diving into specific possibilities, it helps to clarify what a gateway would mean in a physical context. The term is not meant to imply anything fantastical or symbolic. It refers to the idea that the region where relativity fails might connect to another patch of space-time. This connection could take many forms. It could involve a continuation of the collapse into a new region. It could involve a bounce that leads to expansion. It could involve a change in topology that creates an open path. These concepts come from established attempts at quantum gravity, not from metaphorical reasoning. To understand why such possibilities arise in the first place, it's useful to consider the structure of space-time as described by relativity. The theory treats space-time as a manifold, a continuous structure that can be stretched and curved, but maintains coherence. Singularities represent places where the manifold cannot be extended. But quantum gravity models often modify the rules that define the manifold. If those rules change at extremely small scales, the geometry may continue in ways the classical manifold cannot support. One approach comes from the idea of a bounce. In this model, collapse continues until quantum pressure becomes dominant. At that point, further compression is resisted. Instead of stopping permanently, the geometry might rebound. The rebound does not necessarily return matter to its original region. It could produce expansion into a new region of space-time. If this is the case, then the interior of a black hole may connect to something resembling a new domain. Another possibility involves changes in topology. In mathematics, topology describes how regions connect. Relativity assumes space-time has a certain topology. Quantum gravity might allow that topology to shift at extremely small scales. If such a shift occurs, the region originally described as a singularity might open into a new configuration. These ideas are not claims. They are consequences of the frameworks that attempt to unify gravity with quantum rules. They arise because a complete collapse into infinite curvature is not permitted by quantum mechanics. Something must replace it. The possibilities differ depending on the assumptions of each model. Loop quantum gravity is one of the frameworks that produces a bounce-like outcome. In this approach, space-time is treated as discrete. It is made of tiny loops that cannot be compressed beyond a certain limit. When collapse pushes space-time to that limit, the geometry becomes repulsive. This repulsion causes a rebound. The rebound may produce expansion into a new region. In this model, the singularity is replaced by a transition. The geometry contracts, reaches a minimum, and then expands. String theory provides a different perspective. It treats fundamental particles as extended objects rather than points. These objects cannot be compressed into zero volume. When collapse squeezes matter into a region smaller than the size of these objects, the behavior changes. The strings interact in new ways. The internal structure of space-time may shift. Some versions of string theory allow for the possibility that the region inside a black hole connects to another region. This could be viewed as a type of gateway. Another class of models involves quantum modifications to the classical metric. These models do not propose discrete structure or strings. They propose corrections to relativity that become significant at extremely small scales. These corrections smooth out the classical singularity. Instead of infinite curvature, the interior becomes a region with extremely high but finite curvature. This region can continue into a new domain. It does not end. It evolves. The evolution may involve new coordinates or new dimensions. Yet another idea involves the possibility that black holes could connect to white holes. A white hole is a hypothetical object that behaves as the time reverse of a black hole. Instead of trapping matter, it expels matter. Classical relativity allows white holes as mathematical solutions. They appear in extended models of space-time that include wormholes. But classical white holes are unstable. Quantum gravity might stabilize them. In models where black holes transition to white holes, the collapse inside the black hole continues until quantum effects cause a transformation. Matter then emerges into a new region. The transition would be invisible from the outside because the horizon hides the interior. But inside, the evolution could continue smoothly. In this scenario, the singularity is replaced by a doorway between collapse and expansion. These ideas must be handled carefully. They are derived from mathematical models, not from direct observation. The horizon prevents any measurement of the interior. Because of that, the possibilities remain theoretical, but theoretical doesn't mean arbitrary. Each possibility follows from attempts to combine relativity and quantum mechanics consistently. Asking whether singularities could be gateways is not a departure from physics. It is a direct extension of the need to replace a broken equation with a workable one. If the classical singularity represents a failure of the model, then the model must be modified. The modification may allow the geometry to continue past the classical breakdown. That continuation could reasonably be described as a gateway. It's important to clarify what such a gateway would not be. It would not be a portal in the science fiction sense. It would not be an intentional passage. It would not offer control or travel. Instead, it would be the natural continuation of space-time under new rules. It would be a region where classical curvature becomes quantum curvature. The geometry would change in ways the classical model cannot describe, but the transition would still be governed by physical laws. One way to visualize this is to imagine following the collapse mathematically. As the collapse deepens, the curvature grows. The classical model predicts divergence. When corrections are added from quantum mechanics, the divergence is smoothed. The collapse reaches a finite density. The geometry reorganizes. The path forward continues. It does not end. It shifts into a new region. That shift is what some models describe as a gateway. The idea of a gateway arises partly because quantum mechanics does not allow information to vanish. If a black hole could truly destroy information at a singularity, it would violate a core principle of quantum theory. Many researchers take this principle seriously enough to reconsider the fate of collapsing matter. If information cannot be destroyed, then the interior must preserve it. Preservation might require the collapse to continue into a new region, rather than terminating. That continuation could resemble a transition or connection. The information problem is not merely philosophical. It arises from contradictions between relativity and quantum mechanics. Resolving the contradictions often requires altering the picture of the singularity. The altered picture frequently involves new regions of space-time. The reasoning is not based on imaginative desire, but on mathematical necessity. If the equations must preserve information, and if the classical singularity destroys it, then the classical singularity cannot be an accurate description of the interior. Something else must replace it. There are additional models that explore how space-time might behave near the breakdown point. Some propose that space-time tunnels into a new region. Others suggest that quantum fluctuations change the connectivity of space-time. These ideas arise from attempts to solve the equations in ways that avoid infinities. They do not assume anything supernatural. They assume the laws of physics remain consistent. It is also worth noting that the exterior of a black hole remains unchanged in these models. The horizon still forms. The horizon still prevents information from escaping. The geometry outside remains classical. The gateway, if it exists, would be wholly contained within the region hidden from the outside universe. That containment is important. It ensures that no observable contradiction occurs. It maintains consistency with relativity at large scales. Because the interior cannot be observed, no model can yet be confirmed. But the common theme across many frameworks, that the classical singularity is replaced by something finite and evolving, makes it reasonable to ask whether that evolution could lead somewhere beyond the classical description. This is why the question of gateways arises. Thinking of the interior as a continuation rather than an endpoint also fits well with the idea that physics rarely creates final stops. Each time science encountered an apparent stopping point in the past, it eventually discovered a new layer beneath it. Matter was once thought indivisible. Atoms were later found to have internal structure. Then protons and neutrons were shown to contain quarks. Each boundary became a doorway to more structure. Singularities may represent the next such boundary. The difference is that this boundary is marked not by physical observation, but by mathematical breakdown. One limitation is that these possibilities cannot be tested directly. The horizon ensures that no signals escape from the region where the transition would occur. But indirect evidence may appear in the future through gravitational waves or subtle signatures in black hole evaporation. These possibilities motivate ongoing research. For now, the important point is that classical singularities are not likely to be final states. The collapse does not reach a literal point of infinite curvature. The classical model ends at the singularity, but nature does not. The region represents the place where equations must be replaced. Once replaced, the evolution may continue into a new configuration. Discussions about the interior of black holes usually focus on the fact that horizons conceal everything that happens inside them. The breakdown of classical equations, the failure of relativity at extreme curvature, the possible quantum extensions of space-time, all of these remain hidden behind a one-way boundary. Because of that, the details never spill into the surrounding universe. But there is another scenario that has been suggested, one that challenges this comforting separation. It asks what would happen if the breakdown point of classical gravity were not hidden at all. Instead of being tucked safely behind an event horizon, it would sit in plain view. This possibility is known as a naked singularity. The concept raises concern not because the idea is dramatic, but because of what it implies for predictability. Physics depends on being able to determine how systems evolve from their starting conditions. When equations break, predictability breaks. If the breakdown were exposed, then regions of space-time governed by well-tested laws could be influenced by regions where the laws no longer apply. This is the core issue behind the fear of cosmic exposure. The worry is not danger in the cinematic sense. The worry is that determinism would be compromised. Before exploring why this idea is unsettling to physicists, it helps to clarify what a naked singularity would be in classical relativity. Under ordinary collapse, a horizon forms. The horizon ensures that any region where curvature becomes infinite is hidden. Nothing inside can influence the outside, but relativity also allows mathematical solutions in which no horizon forms. In those solutions, the region of divergence is visible. Light and particles can travel from the singularity to the rest of space-time. Relativity does not forbid these solutions mathematically. They are legitimate outcomes of the equations. The concern arises from what they represent. These solutions were first examined in depth through work by mathematicians and physicists analysing gravitational collapse. They found that under certain idealised conditions, a collapsing object could form a singularity without producing a horizon. This would expose the breakdown point. The exposure would allow signals originating from regions of infinite curvature to reach the outside universe. That is the essence of a naked singularity. But because singularities represent the failure of classical equations, any signal coming from such a region would be impossible to describe within the theory. The behaviour of the signal would be unpredictable. The classical laws would not apply. In effect, the region would inject unpredictability into the universe. To avoid this scenario, a principle was proposed known as cosmic censorship. The idea is straightforward. It claims that in realistic physical situations, horizons always form around singularities. The breakdown regions remain hidden. Naked singularities do not appear in nature. They might exist mathematically, but they are prohibited physically. This principle remains unproven, but many researchers accept it as a reasonable expectation because it preserves the stability of physical law. Understanding why cosmic censorship matters requires considering how physics relies on predictability. When the evolution of a system can be calculated, initial conditions determine future behaviour. Relativity upholds this structure. If a singularity were visible, the region where laws fail could influence other regions. That influence would be impossible to calculate. The failure would spread. Predictions would lose reliability. The laws would no longer govern all regions of space-time. This concern is not philosophical. It is mathematical. In a spacetime containing a naked singularity, the equations describing motion and curvature would have undefined values in regions that affect the rest of the universe. That means the equations could not uniquely determine the future. The core machinery of physics would no longer function. This is why the possibility of naked singularities introduces unease among theorists, but it also creates opportunities to explore the boundaries of relativity. Studying when and how they might appear provides insight into the limitations of the theory. It also reveals much about the structure of collapse and the conditions required for horizons to form. To see how a naked singularity might arise in classical models, consider a collapse that lacks symmetry. Most textbook examples assume spherical symmetry because these cases are mathematically manageable. But real astrophysical collapse is rarely perfectly symmetrical. It can be uneven, it can rotate, it can fragment, it can develop instabilities. In certain models of asymmetric collapse, curvature can diverge before a horizon forms. That divergence exposes the breakdown region temporarily. If no horizon forms quickly enough, the singularity becomes visible. Another scenario involves extremely rapid rotation. A rotating black hole is described by a solution known as the Kerr metric. In this solution, the presence of spin modifies the structure around the collapse. If the spin is high enough, the equation suggests that the horizon may not form. Instead, the singularity might be exposed, but achieving this condition would require spin so extreme that it may not occur in nature. Most astrophysical processes remove angular momentum as collapse deepens. That removal likely prevents the exposure. Even though these extreme cases may not occur naturally, examining them provides valuable insight. They show how delicate the balance is between collapse and horizon formation. They reveal the need for specific conditions. They highlight the role of angular momentum, density distribution, and perturbations. They also help clarify why cosmic censorship is plausible even if unproven. Another reason the idea of naked singularities draws interest is the possibility that quantum corrections could change how horizons behave. If quantum gravity prevents classical singularities, it might also influence the formation of horizons. Some models suggest that quantum effects could delay horizon formation. If the delay is long enough, a portion of the collapse might be visible before being hidden. This would produce temporary exposure, though not exposure of infinite curvature. Instead, it would expose quantum-dominated regions. These possibilities push the boundaries of what physics can describe. They highlight how strongly our understanding depends on horizons. With horizons in place, the breakdown remains isolated. Without them, the breakdown spreads outward into regions where physics should remain predictable. This is why exposure is such a pressing concern. The debate around cosmic censorship is not about whether singularities exist. It is about whether they can influence regions where classical physics still applies. If they remain hidden, all predictions outside remain intact. If they become exposed, the predictions break. Testing cosmic censorship directly is nearly impossible. Naked singularities, if they existed, would produce signals of undefined structure. Those signals might appear chaotic or inconsistent with known physical processes, but distinguishing such signals from high-energy astrophysical phenomena would be difficult. Additionally, the theoretical status of singularities complicates any attempt to interpret such signals. For these reasons, research often focuses on the underlying mathematics. By studying the equations governing collapse, physicists try to determine whether naked singularities arise naturally. Many studies suggest that under small perturbations, horizons still form. This finding supports cosmic censorship. But other studies show that certain conditions might produce exposure. These findings keep the debate active. Regardless of which side proves correct, the discussion reveals important truths about how sensitive spacetime is near gravitational extremes. It shows how small changes in conditions can radically alter outcomes. It highlights the tight interplay between geometry, matter, and motion. It also underscores how much remains unknown about the final stages of collapse. Quantum gravity might ultimately resolve the question. If quantum mechanics prevents infinite curvature, then the classical singularity never forms. Instead, the region becomes quantum-dominated. That region might remain hidden behind a horizon, or quantum effect could modify horizon formation. In either case, the concept of naked singularities would need reinterpretation. The question becomes, could a quantum-dominated region be exposed? Most models suggest that exposure would still be unlikely. Horizon formation is robust under many conditions. Even if the interior structure is replaced, the boundary that hides it may remain. This robustness provides some reassurance, but until the quantum description is known, the question cannot be settled fully. One important aspect of the discussion is the distinction between what the theory predicts and what nature allows. Mathematics permits solutions with exposed singularities. Nature may not. Many mathematical solutions to physical equations represent unphysical configurations. For example, negative mass solutions exist mathematically but are not believed to exist physically. Naked singularities may be another case where the mathematics extends into scenarios the universe does not realize. Understanding these distinctions requires careful analysis. Researchers must determine whether the conditions needed for naked singularities are stable. If the conditions are unstable, then the slightest perturbation would cause horizons to form. In that case, naked singularities would be mathematically interesting but physically irrelevant. If the conditions are stable, then exposure could occur. The stability analysis is ongoing. Rotation, magnetic fields, turbulence, and energy flows all influence collapse. The role of each must be examined. Even small changes can alter the outcome. The complexity of realistic collapse makes the question challenging. This complexity may be one reason nature avoids exposure. The conditions required for naked singularities may be too strict to realize. Despite the uncertainties, the concept remains valuable. It forces theorists to confront the limits of predictability. It tests the boundaries of relativity. It challenges assumptions. It motivates exploration of quantum gravity. It keeps attention on the need to replace the classical singularity with a complete description. Exposure is feared not because it implies danger, but because it threatens the consistency of physical law. A predictable universe requires that the breakdown of equations remain hidden. Naked singularities would remove that boundary. They would allow undefined regions to influence defined regions. That influence would undermine the equations that describe motion, curvature, and causality. It would represent a fundamental gap. Even if nature avoids this outcome, contemplating it reveals how crucial horizons are for preserving the structure of physics. Horizons act as buffers. They isolate regions where different rules apply. They allow classical gravity to operate on large scales while quantum gravity governs small scales. They maintain order. Attempts to understand what really happens where relativity reaches its limits always lead to the same conclusion. The theory that describes gravity so successfully in nearly every context is incomplete. It works for planets, stars, galaxies, and even large regions inside black holes. It explains orbits, gravitational waves, and the bending of light. It predicts time dilation and describes the structure of spacetime with impressive accuracy. But at the point where curvature grows beyond what the equations can handle, relativity stops being a reliable guide. The model produces infinities. Those infinities indicate that something essential is missing. That missing piece is the physics we still do not have. The unfinished nature of gravity is not a minor detail. It sits at the center of nearly every major mystery in modern physics. Questions about the origin of the universe, the interior of black holes, and the behavior of space-time at extremely small scales all depend on the same missing framework. Without that framework, singularities remain mathematical placeholders. They mark the boundaries where classical understanding ends, but they say nothing about what lies beyond. To see why the missing physics is so important, consider how different theories describe different scales. Quantum mechanics handles the small scale. It explains the behavior of atoms, electrons, photons, and other fundamental particles. It describes uncertainty, superposition, and entanglement. It works well for systems where distances and energies remain within certain ranges. General relativity handles the large scale. It explains gravity as curvature. It describes how mass and energy shape spacetime. It works well for systems with strong gravitational fields or large structures. But the universe contains regions where both small scales and strong gravity combine. Those regions require a theory that unifies quantum rules with curvature. Such a theory does not exist yet. This gap becomes especially clear when studying the interior of a black hole. Relativity predicts a breakdown. Quantum mechanics predicts that matter cannot collapse indefinitely. Only a theory that merges both can describe the final stages. Each attempt to build such a theory must satisfy strict requirements. It must reduce to relativity when gravitational fields dominate. It must reduce to quantum mechanics when small-scale effects dominate. It must remain consistent with the principles of both. It must avoid infinities. It must preserve information. And it must allow space-time to behave in a well-defined way, even under extreme conditions. Meeting all these requirements is not easy. Many attempts have been made, but none have achieved full acceptance. The search continues because the universe demands a consistent description. Singularities highlight exactly which regions require that description. It helps to look at the history of how physics progressed to understand why the missing framework is so significant. Earlier theories reached similar limits. Classical mechanics failed to describe atomic behavior. This failure led to quantum mechanics. Newtonian gravity failed to describe strong gravitational fields. This failure led to general relativity. Each time, the breakdown showed where the next theory was needed. Singularities play the same role today. They mark the place where relativity fails. They show where the next theory must take over. One approach toward building this missing framework is known as loop quantum gravity. It attempts to quantize spacetime itself. Instead of treating spacetime as continuous, it treats it as composed of small units. These units bond into networks that form the fabric of spacetime. Under this framework, curvature cannot reach infinity, because spacetime cannot be subdivided indefinitely. This avoids the singularity. The collapse reaches a minimum size and then transitions into a new phase. The details of this transition vary depending on how the theory is applied, but the essential point is the same. The singularity is replaced by something finite. Another approach comes from string theory. It assumes that the smallest building blocks of the universe are not point particles, but tiny one-dimensional strings. These strings vibrate at different frequencies to produce different particles. Because strings have size, they cannot be compressed into zero volume. This prevents the formation of a classical singularity. The collapse leads to a region where strings interact intensely. The internal geometry may change. Some versions of the theory predict that spacetime could continue into additional dimensions. Others propose that black holes could connect to new regions. The nature of the transition depends on the version of the theory. A third approach involves modifying general relativity itself. These modifications add correction terms to the equations that become important at extremely small scales. They smooth out the curvature. Instead of diverging, the curvature reaches a maximum value. The collapse reaches an endpoint that is finite. The endpoint could resemble a dense core. It could resemble a transitional region. It could behave like a different phase of spacetime. These models share the key property that they eliminate infinities while preserving consistency with classical behavior at larger scales. Despite these attempts, no model has achieved universal acceptance. Each approach has strengths and weaknesses. Each approach explains some phenomena well but struggles with others. This lack of consensus is one reason the physics remains unfinished. The universe may follow rules that differ from any current proposal. Until a complete theory is discovered, the true nature of the singularity remains unknown. One reason the search for a unified theory is challenging is that gravity behaves differently from the other fundamental forces. Electromagnetism, the weak force, and the strong force all fit naturally into quantum mechanics. Gravity does not. Attempts to quantize gravity directly run into difficulties. The mathematics becomes unstable. The results diverge. These divergences resemble the infinities produced by singularities. The problems may be connected. If gravity is inherently geometric, then quantizing it may require quantizing geometry itself. This is one reason loop quantum gravity treats spacetime as discrete. But whether spacetime is truly discrete remains uncertain. Another challenge involves information. Quantum mechanics demands that information cannot be destroyed. Relativity suggests that information falling into a black hole becomes inaccessible. Hawking radiation introduces further complexity. It allows black holes to evaporate slowly. If a black hole evaporates completely, what happens to the information it once contained? If the information disappears, quantum mechanics is violated. If the information remains somehow encoded, relativity must be modified. This conflict is known as the information paradox. Solving the paradox requires the unfinished physics of quantum gravity. The singularity sits at the heart of this conflict. If the singularity were physical, information reaching it would be destroyed. That outcome cannot be allowed under quantum rules. Therefore, the singularity must be replaced by something that preserves information. But without a theory of quantum gravity, the replacement remains unknown. Various proposals exist, but none have been proven correct. Some researchers suggest that information escapes through subtle correlations in Hawking radiation. Others suggest that the horizon stores information on its surface. Some propose that the interior geometry encodes information in ways that remain consistent during evaporation. Each of these proposals requires modifications to our current understanding. All of them highlight the incompleteness of existing theories. The need to unify relativity and quantum mechanics extends beyond black holes. It also applies to the earliest moments of the universe. The Big Bang represents another region where classical equations produce a singularity. That singularity likely represents the same kind of breakdown as the one inside black holes. The early universe probably entered a quantum gravitational phase where spacetime behaved differently. That phase remains unknown because the necessary physics remains unfinished. The structure of spacetime at the earliest moment cannot be described using classical equations. It requires quantum gravity. Understanding this missing phase would reveal how the universe began. It would reveal whether spacetime had a beginning or transitioned from something else. It might show whether the early universe underwent a bounce. It might show whether spacetime expanded from a compact region. Without quantum gravity, the answers remain inaccessible. The unfinished nature of the physics also affects our understanding of vacuum energy. Quantum mechanics predicts fluctuations that fill space. These fluctuations influence spacetime, but relativity does not incorporate them consistently. Combining these influences requires a unified framework. The singularity problem is tied to these vacuum effects. At extremely small scales, vacuum energy becomes significant. It alters curvature. It influences collapse. Without a unified theory, these effects cannot be fully described. Another area affected by the unfinished physics is the structure of space-time itself. Relativity treats space-time as smooth. Quantum mechanics suggests that space-time might fluctuate. These fluctuations could alter the geometry at small scales. They could produce foam-like behavior. They could change how distances behave. Understanding these fluctuations requires quantum gravity. The need for a unified theory is reinforced by the way singularities force the issue. If singularities were merely rare mathematical curiosities, the urgency might be lower. But they appear in every complete collapse. They appear in the earliest universe. They emerge from well-established equations. They do not depend on unusual conditions. This consistency indicates that the missing physics is fundamental. One important aspect of the search for quantum gravity is the requirement that the new theory must remain compatible with known observations. It cannot alter classical gravity in regimes where relativity works well. It cannot modify quantum mechanics in regimes where quantum rules work well. It must fit both without contradiction. This dual requirement makes the task more difficult, but it also ensures that the final theory, once discovered, will be comprehensive. Many researchers expect that the final theory will contain elements of both continuity and discreteness. It may allow spacetime to behave smoothly at large scales but granularly at small scales. It may unify the mathematical structure of fields and geometry. It may provide a consistent framework for curvature and quantum behavior. It may eliminate singularities entirely. Even though the search remains unfinished, progress continues. New mathematical techniques, observational data from gravitational waves, and improvements in particle physics all contribute to the effort. Each new insight brings the physics closer to completion. Singularities serve as both obstacles and guides. They expose the limits of current models. They highlight where the next developments must occur. The interior of a black hole represents one environment where these developments are essential. The early universe represents another. Both require the same unfinished physics. That connection suggests that the final theory will unify many seemingly unrelated concepts. It may reveal common principles underlying both collapse and expansion. It may show how space-time behaves when pushed to its limits. As you sit with these ideas, it becomes clearer why singularities are so influential. They force physicists to confront unfinished work. They highlight the missing foundation. They mark the places where classical descriptions stop. And they point toward the need for a deeper, more complete framework. Work on black holes often leads naturally to a comparison that is difficult to ignore. If the collapse of a massive star brings space-time to conditions where classical equations fail, then what about the earliest moments of the universe? The equations describing the expanding cosmos, when tracked backwards, reveal a point where density and curvature rise without bound. This resemblance has been apparent since the first models of cosmic expansion. The idea that our universe emerged from a region resembling a singularity is not an interpretation layered on top of the equations. It comes directly from the mathematics. Yet, just as with black holes, the singularity at the beginning of the universe should not be taken as a literal physical point. It marks a place where the equations stop providing meaningful answers. Before considering what this tells us about the origins of the universe, it helps to review how the current model describes cosmic expansion. Observations of distant galaxies show them moving away from us. Their motion follows a pattern that suggests space itself is expanding. This expansion applies everywhere, not just near Earth. The galaxies are not moving through a fixed background. The background is stretching. When the equations that describe this expansion are reversed, the stretching decreases. Further backward, the universe becomes smaller. Eventually, the equations produce a region of extremely high density. That region, if described purely with classical tools, becomes a singularity. This conclusion comes from the same problem encountered with black holes. Relativity assumes a smooth space-time. It assumes the structure can be divided indefinitely. It assumes that curvature can rise without hitting a physical limit. These assumptions fail when compression becomes extreme. In the early universe, compression becomes extreme everywhere. The curvature predicted by the classical model grows rapidly. The equations begin approaching infinite values. The singularity appears. Once it appears, the classical model can no longer describe what came before. Despite the mathematical similarity to black holes, the environment of the early universe differs in important ways. Inside a black hole, the collapse occurs in a region isolated by a horizon. In the early universe, no horizon separates anything. The entire region is accessible. There is no exterior. The collapse is not directed toward a central point. Instead, the entire volume contracts uniformly. The geometry behaves differently. But the underlying issue remains the same. Classical relativity cannot extend to the earliest moment. Because the classical singularity does not represent a real physical state, the question arises, what did the universe look like before the breakdown? Or more precisely, what did the universe transition from? Many approaches to quantum gravity provide possible answers. They differ in their interpretations, but they share the idea that the classical singularity must be replaced with something finite. They agree that the earliest universe was dominated by quantum gravitational effects, and they agree that spacetime behaved differently at those scales. To understand why this matters, it helps to consider how the early universe evolved once it expanded enough for classical physics to apply. After the earliest phase, the behavior becomes easier to describe. Temperatures drop, particles form, forces separate, atoms assemble, stars and galaxies eventually emerge. Every stage of this evolution depends on the initial conditions produced by the earliest moment. If the singularity is not literal, then the universe's beginning must contain structure that classical models cannot see. That structure may influence everything that followed. One possibility is that the universe began with a bounce rather than a singular beginning. In bounce models, the universe undergoes contraction prior to expansion. The contraction continues until quantum gravitational effects prevent further collapse. At that point, the geometry reverses. Expansion begins. This replacement eliminates the singularity. The earliest moment becomes a transition rather than a beginning. The universe before the bounce may have been large. It may have had structure. But because the bounce occurs at high curvature, details of the prior state may be difficult to retrieve. Another possibility is that the universe emerged from a compact region of space-time without undergoing a classical collapse. In this scenario, quantum fluctuations dominate the earliest phase. Space-time might have existed in a form that does not resemble the smooth structure described by relativity. It may have undergone transitions between different configurations. The expansion we see today would be one of those transitions. Other models propose that the early universe expanded from a state where space-time had different dimensional behavior. In these models, the early geometry may have had fewer effective dimensions. As expansion progressed, additional dimensions became accessible. The apparent singularity arises because classical equations do not account for these altered structures. Even within the standard framework of inflationary cosmology, the classical singularity is recognized as a boundary where the theory must eventually be replaced. Inflation describes how the universe expanded rapidly in its earliest moments. It explains many observed features, such as the uniformity of the cosmic microwave background and the distribution of galaxies. But inflation does not describe what came before it. It assumes an initial state that remains unexplained. That initial state cannot be a singularity in the physical sense. It must correspond to a region where quantum gravitational behavior dictated the structure. The resemblance between black hole singularities and the initial singularity raises another question. Could the beginning of the universe be connected to the interior of a black hole? This idea has appeared in several theoretical proposals. In these proposals, the interior of a black hole might undergo a transition. Instead of collapsing into a physical singularity, the geometry might rebound or tunnel. The rebound could produce expansion in a new region of space-time. That new region could resemble a universe. In such a scenario, our universe might exist inside the extended geometry of another universe. The singularity at the beginning would be a disguised form of the breakdown predicted by relativity. These proposals do not claim to describe the universe's true origin. They illustrate how the breakdown point of classical gravity might function as a transition rather than an endpoint. They show how quantum corrections could allow new regions to form. They highlight the need for a unified framework. One important consequence of these ideas is the realization that the early universe may not have needed to begin from a perfect point. It might have emerged from a state where quantum fluctuations determine the distribution of energy. These fluctuations could seed the structure that later formed galaxies. They could influence the temperature variations in the cosmic microwave background. They could establish the initial conditions for the observed universe. The breakdown of classical physics does not prevent meaningful structure from emerging. It prevents classical equations from describing that emergence. Another aspect to consider involves entropy. The early universe had extremely low entropy. This low entropy state is unusual. It requires explanation. If the universe emerged from a bounce or a quantum gravitational transition, the low entropy could be a natural consequence. Certain models suggest that the prior contraction reduces entropy. Others suggest that the quantum-dominated state has minimal entropy. In either case, the singularity-like beginning is replaced with a structured initial condition. Efforts to explore these ideas rely heavily on the mathematics of quantum cosmology. This field attempts to apply quantum mechanics to the universe as a whole. It treats the geometry and matter as quantum variables. The equations governing these variables differ from classical equations. They include uncertainty. They include discrete behavior. They include probability distributions that describe how the universe might have transitioned into its expanding phase. Some of the proposed models involve wave functions that describe the universe. These wave functions evolve according to rules that combine quantum physics and cosmology. They do not produce a classical singularity. Instead, they produce a region where geometry becomes uncertain. The uncertainty resolves into expansion when classical behavior takes over. Other models explore the idea that spacetime might not have a meaningful before the earliest moment. In these models, time itself might emerge with the expansion. The singularity then represents a boundary where time loses definition. The universe does not originate from a prior state. It originates from a region where classical time does not exist. This concept is not meant to be philosophical. It arises from the behavior of time in quantum gravity. If time becomes ill-defined at extremely small scales, then asking what happened before may not have meaning. This idea helps explain why the singularity appears in the classical equations. The equations assume continuous time, but quantum gravity may not. If time is not continuous at extremely small scales, the classical equations naturally break. The breakdown then reflects the fact that the assumptions of the equation no longer apply. Understanding the early universe requires replacing those assumptions. Quantum gravity must provide a description where time and space are both treated as quantum variables. Only then can the earliest moment be described accurately. Until such a theory is complete, the classical singularity remains a marker. One of the most intriguing questions about the early universe involves the shape of space-time at its beginning. Observations show the universe is nearly flat. That flatness requires precise initial conditions. Inflation helps explain this flatness by stretching space-time, but even inflation requires an initial state. The classical singularity cannot provide that state. A quantum gravitational description must do so. Several models propose that flatness emerges naturally from the behavior of quantum space-time. In some models, space-time is forced toward flatness by the rules governing quantum geometry. In others, fluctuations average out. In still others, the earlier state is constrained to be flat by symmetry. These explanations remain provisional until a full theory is known, but they show how the singularity problem connects to many other questions. The beginnings of the universe also involve the origins of matter. In classical models, matter density becomes infinite at the singularity. Quantum gravity avoids that result. It allows a finite density. It allows fields to fluctuate. It allows energy to distribute in ways that seed future structure. Matter could emerge through transitions in quantum fields. These transitions require physics beyond the classical picture. Another important issue involves the total energy of the universe. Classical models struggle to describe it. Quantum models may provide better explanations. They may show how energy conservation works in expanding space-time. They may show how energy emerges from fluctuations. They may explain why the universe exists with the properties it has. Because the earliest moment cannot be observed directly, the search for answers depends on indirect evidence. Observations of cosmic microwave background radiation, gravitational waves, and large-scale structure help constrain models. Each observation narrows the possibilities. Each observation reduces the range of acceptable theories. Even though the earliest moment remains hidden, its effects remain visible. These effects guide the search for the missing physics. The connection between black hole singularities and the initial singularity reveals a deeper point. Singularities appear wherever classical gravity is pushed to extremes. They appear when space-time is compressed. They appear when curvature grows. They appear when equations assume continuity that cannot be maintained. That consistency across cosmic scales indicates the need for a unified description. The universe uses one set of rules. The models used to describe it must eventually match that unity. The earliest moment of the universe represents the most extreme test of that unity. It requires combining quantum fluctuations with gravitational curvature. It requires replacing the classical singularity with a quantum description. It requires understanding how space-time behaves at its limits. Arguments about the nature of singularities often begin with a straightforward observation. Every time general relativity is pushed to its limits, the same outcome appears. The equations predict a point where curvature grows without bound. The metric becomes undefined. Distances collapse to zero. Pathways terminate abruptly. None of these features resemble ordinary physical behavior. They look instead like indications that the model has been carried past the region where its assumptions hold. Because of this, one of the most persistent questions in gravitational physics is whether singularities correspond to something real in the universe, or whether they represent the limits of our current descriptions. Rather than starting with an immediate answer, it helps to examine what the equations are actually doing when they produce infinite curvature. Relativity treats space-time as a smooth manifold. It assumes that distances can be subdivided indefinitely. It assumes that curvature can be described at every scale. These assumptions work well when curvature remains moderate. They work for stars, planets, and galaxies. They work for gravitational waves and cosmological expansion. But when space-time is compressed into extremely small regions, the assumptions stop being reliable. The infinities produced by the equations do not reflect physical infinities. They reflect the failure of the underlying assumptions. The appearance of singularities in relativity is therefore more reminiscent of a calculation reaching a domain error than a prediction of a physical object. When a theory predicts infinite temperature, infinite density, or infinite curvature, it is usually signaling that something is missing. The theory needs to be extended. That kind of signal has appeared repeatedly in the history of physics. Classical descriptions of the atom predicted electrons collapsing into the nucleus. That prediction did not represent physical collapse. It represented the need for quantum rules. In the same way, the singularities of relativity represent the need for quantum gravity. Even knowing this, the question persists because relativity treats singularities seriously. They arise naturally from the equations. They appear in solutions describing gravitational collapse. They appear in solutions describing the expanding universe. They appear whenever the geometry is pushed to its limits. The theory does not mark them as calculation errors. It marks them as endpoints. But endpoints are not necessarily physical. They can indicate where a theory stops being applicable. To evaluate whether singularities correspond to real features of the universe, one must consider what it would mean for them to exist physically. A physical singularity would represent a region where space-time curvature becomes infinite. That means the metric cannot describe distances or times. It means no extension of space-time is possible. It means the laws governing motion cease to apply. This interpretation conflicts directly with what is known about quantum physics. Quantum mechanics forbids perfect localization. It forbids zero volume. It forbids infinite energy density. A real singularity would violate these principles. The violation suggests that the classical prediction cannot be literal. Another way to address the question is to examine what relativity predicts about regions near a singularity. The approach to the singularity can be described mathematically until the final moment when the curvature diverges. But relativity does not describe what happens at the singularity itself. It provides no evolution beyond it. The equations do not allow the collapse to pass through that point. This is another sign that the singularity is a confession of mathematical inability rather than a physical feature. Still, the issue becomes more subtle when considering whether nature could approach a singularity asymptotically without reaching it. Perhaps quantum corrections become important before the singularity forms. If those corrections modify the interior, the collapse could reach a finite state where curvature reaches a maximum. That state would not be a singularity in the classical sense, it would be a quantum gravitational region. This interpretation aligns with most current attempts to build a unified theory. In these attempts, curvature grows large but not infinite. The classical singularity disappears. The region becomes dominated by quantum behavior. Because no unified theory of quantum gravity exists yet, the classical singularity remains in the equations. The equations continue to present it as the endpoint. But the presence of this endpoint is not evidence that the universe contains physical infinities. It is evidence that relativity needs assistance in those regimes. One reason the conversation persists is that singularities appear consistently in solutions that describe realistic gravitational collapse. This consistency raises the question of whether nature produces something that resembles a singularity, even if the literal infinite value is not physical. The answer depends on what counts as resembling a singularity. If the final state of collapse is a region of extremely high but finite curvature, one could argue that the singularity predicted by relativity points toward that region. It identifies where quantum physics must take over, but it does not describe the region accurately. It only marks the location where the classical description stops. Examining how singularities are treated in different theoretical frameworks helps clarify the issue further. In loop quantum gravity, the singularity is replaced by a minimum volume. Space cannot be subdivided indefinitely. Curvature cannot diverge. Instead of becoming infinite, the collapse reaches a point where the geometry transitions. In this picture, the classical singularity is replaced. It becomes a region where the geometry behaves differently. It is not a point of infinite curvature. It is a point where the underlying structure of space-time changes. String theory offers another interpretation. It replaces point particles with extended objects. These extended objects cannot be compressed into zero volume. Their size creates a limit on how small the region can become. The curvature does not diverge. Instead, the interior becomes a region where string interactions dominate. This region replaces the classical singularity. It is not infinite. It is finite. It is structured. It is governed by quantum rules rather than classical ones. Other models introduce quantum corrections to general relativity. These corrections modify the behavior of curvature. They prevent singularities by smoothing out the geometry. The collapse reaches a peak curvature and then transitions into a different configuration. No infinite values arise. The collapse does not terminate abruptly. It continues under new rules. These interpretations share a common theme. They all replace singularities. Not one accepts a singularity as a literal physical entity. This consistency across competing approaches suggests that singularities are confessions of mathematical insufficiency. They are the equations admitting they cannot describe the region adequately. However, the question becomes more nuanced when considering what is observable. The horizon surrounding a black hole prevents direct observation of the interior. Whatever replaces the classical singularity remains hidden. Because of this, the mathematical confession cannot be tested directly. The presence or absence of a true singularity inside a black hole may never be observable. If quantum gravity prevents singularities, then the breakdown region remains inaccessible. If relativity's singularity was somehow physical, it would remain inaccessible as well. In either case, the horizon blocks observation. This raises a deeper point about what it means for something to be real. If a region cannot be observed and cannot influence anything outside the horizon, its properties may be unknowable. The interpretation of the singularity becomes a question about the consistency of the theory, rather than the literal structure of the interior. What matters is not whether the singularity exists physically, but whether the theory describing space-time remains consistent. In that sense, singularities are signals to physicists more than predictions. They indicate where the classical model breaks, They identify where quantum gravity must begin. They provide direction for future research. They reveal that certain assumptions in relativity are insufficient when curvature becomes extreme. Singularities also appear in the equations describing the early universe. The equations predict a singularity at the beginning of cosmic expansion. But just like black hole singularities, the early universe singularity is widely interpreted as a mathematical confession. It indicates that classical equations cannot describe the earliest moment. It does not describe an actual infinite density state. Quantum cosmology replaces the classical singularity with a structured beginning. That beginning may involve a bounce. It may involve a quantum transition. It may involve an emergent form of spacetime. In none of these cases does the singularity represent a physical point. Considering how consistently singularities are replaced across different models, it becomes difficult to argue that they represent physical objects. They appear to represent the opposite, moments when a missing theory must take over. But the discussion is not entirely one-sided. There are reasons some researchers continue to treat singularities as useful idealizations. In classical models, singularities provide a reference point. They mark the center of the collapse. They simplify calculations. They help describe the geometry in regions where curvature increases rapidly. These uses make singularities mathematically convenient even if they are not physically meaningful. Another reason singularities remain part of the discussion is that relativity itself does not forbid them. It predicts them. The theory does not contain internal contradictions when singularities appear. From a purely classical perspective, singularities are legitimate endpoints. They represent legitimate solutions. Because of this, some researchers hesitate to dismiss them entirely. They argue that the singularity might be a real feature of the classical theory, even if it is replaced in the quantum theory. This distinction is important. The classical singularity is a feature of relativity. The quantum-corrected state that replaces it is a feature of quantum gravity. Both interpretations can be correct within their domains. The singularity is real in the sense that it marks a failure of the classical theory. It is not real in the sense of representing a physical entity. Thinking of singularities as mathematical confessions captures the situation well. They confess the limitations of the theory. They reveal where assumptions fail. They show where the next theory must take over. They do not describe actual infinities. This interpretation does not diminish the importance of singularities. The regions near them remain the most interesting regions in gravitational physics. They reveal where unknown physics must govern. They point toward the necessity of quantum gravity. They highlight the regions where the universe brings classical tools to their limits, even though the true nature of the interior remains hidden behind horizons or lost in the earliest moments of cosmic history. The need for a complete description persists. The singularity question drives the search. It motivates the development of new frameworks. It clarifies which assumptions need revision. It links cosmology with black hole physics. It ties together gravitational collapse and cosmic expansion. Pulling back from the detailed arguments about whether singularities are physical or mathematical brings the entire discussion into a clearer perspective. At each stage of examining collapse, curvature, horizons, and the limits of classical equations, one theme has remained constant. Every attempt to understand what happens in extreme gravitational environments eventually leads back to the same underlying issue. Physics has reached a boundary. The theories that describe the universe so precisely at accessible scales cannot be stretched indefinitely. Once those limits are reached, new rules must take over. Reviewing the path taken so far makes this limitation easier to see. General relativity explains gravity as the curvature of space-time. It works for stars, galaxies, and the observable universe. It works for gravitational waves and black hole mergers. Yet the moment the model is applied to regions of extreme compression, it produces results that are difficult to interpret physically. Curvature grows without limit. Geodesics terminate. The metric becomes undefined. These outcomes point unmistakably toward the need for a deeper description. Quantum mechanics, on the other hand, governs the behaviour of atoms and particles. It handles uncertainty, superposition, and entanglement. It explains why electrons occupy stable states. It explains how photons behave. But quantum mechanics does not include gravity. It does not describe curvature. It does not explain spacetime itself. Both theories are extremely successful, but neither can replace the other. When conditions demand both simultaneously, neither one can provide a complete answer. Examining singularities has shown how clearly this limitation appears. In black hole interiors, relativity predicts a breakdown of its own structure. In the earliest state of the universe, relativity again predicts a breakdown. The same warning appears in both contexts. The singularity is not the universe revealing a mysterious object. It is the theory revealing its own boundaries. Looking at the range of attempts to replace the singularity with a finite, physically meaningful region further confirms this view. Whether through discrete geometry, extended objects, quantum corrections, or entirely new frameworks, each attempt eliminates infinite curvature. Each attempt restores consistency by introducing new rules. Each attempt shows that singularities are not likely to be part of nature. They are likely to be signs that the classical model becomes incomplete. Returning now to the larger scale helps place these details into context. Singularities appear only when pushing toward extremes. For almost all observable environments, relativity remains sufficient. Space does not collapse into infinite curvature in normal conditions. Galaxies evolve without reaching mathematical boundaries. Stars live and die without creating singularities except in highly specific circumstances. The cosmos, in its everyday behaviour, follows the rules of relativity without complication. Even gravitational collapse into black holes follows relativity cleanly, until the interior reaches the region where quantum gravity is required. Outside the horizon, the model performs flawlessly. Observations of black hole mergers confirm its predictions. The horizon hides whatever corrections are needed inside. This makes it possible to rely on relativity for a vast range of calculations. Stepping back in this way emphasizes how localized the missing physics is. The breakdown occurs at the smallest possible scales and in the strongest possible gravitational fields. This narrow region is difficult to access, both observationally and experimentally. Because horizons isolate black hole interiors, direct measurement remains impossible. Because the earliest universe cannot be revisited, its initial state must be inferred. These constraints ensure that the missing framework will take time to develop. Even so, progress happens steadily through indirect means. Observations of gravitational waves allow tests of extreme conditions. Measurements of the cosmic microwave background reveal the imprint of early universe fluctuations. Experiments in particle physics probe interactions that might be connected to quantum gravity. Each piece of data adds constraints. Each constraint narrows the possibilities. Each narrowing helps shape the future theory. Returning gradually to the broader theme also highlights how much of the universe remains governed by known physics. Galaxies orbit their centers. Stars fuse hydrogen. Planets follow predictable paths. Molecular clouds collapse into new stars. None of these processes require quantum gravity. They unfold according to rules that have been tested repeatedly. This does not diminish the importance of the missing physics, it simply places it in perspective. The regions near singularities represent a tiny portion of space-time, yet they hold disproportionate importance because they reveal where understanding must expand. These regions serve as guides. They mark where future theories must operate. They provide direction for the next steps in physics. Looking again at the question that motivated much of this journey, whether singularities exist physically or are mathematical signals, it becomes clear that the most meaningful answer lies somewhere between those two interpretations. Singularities are real in the sense that they appear consistently in the classical equations. They mark locations where the model fails. They are not real in the sense of representing physical points with infinite curvature. They are warnings. They are boundaries. They are the signs that physics must be expanded. Returning from this detailed examination of collapse and curvature, it becomes easier to see how the broader universe fits together. Most of space-time is stable. Most of space-time is describable with classical tools. The extreme environments discussed earlier are exceptions. They reveal the edges of the map. They show the frontier where new physics must be developed. Even the early universe, which appears to contain a classical singularity when traced backward, becomes less mysterious when framed this way. The first fraction of a second remains beyond complete understanding, but everything after that follows patterns that can be described with great precision. The structure of galaxies, the distribution of large-scale matter, the temperature variations in the cosmic microwave background, and the patterns in gravitational lensing all provide evidence of the early universe's evolution. These observations confirm that the classical singularity is not a physical state. It is a placeholder for missing physics. Gradually shifting focus from specific mechanisms to overall patterns helps reinforce the continuity between ordinary physics and the unresolved regions. Although the interior of a black hole cannot be observed, the exterior behaves predictably. Although the earliest moment cannot be recreated, the later evolution carries its imprint. These connections show how the unknown and known regions remain linked. Moving away from the details of quantum gravity proposals and classical breakdowns also brings attention back to the role that scientific models play. Models are tools designed to explain observations and predict future behavior. They are not literal descriptions of reality. Relativity excels as a tool for describing curvature. Quantum mechanics excels as a tool for describing particles. Each tool performs well within its domain. Where the domains overlap, new tools must be built. Singularities signal where those new tools are required. One of the most reassuring aspects of physics is that each time models break down, the breakdown leads to deeper understanding. Classical mechanics gave way to quantum mechanics. Newtonian gravity gave way to relativity. These transitions did not erase previous knowledge. They extended it. They connected the old with the new. The same process likely awaits the problem of singularities. Quantum gravity, when complete, will not discard relativity. It will extend it. It will retain the parts that work and modify the parts that fail. It will treat singularities not as physical objects, but as indicators of where adjustments are needed. Considering the overall structure of the universe in this light helps calm the urgency that sometimes surrounds questions about singularities. The universe has remained stable for billions of years. The formation and evolution of stars, galaxies, and cosmic structure occurs without requiring knowledge of the missing physics. The regions where new rules must operate are extremely limited. They matter because they reveal frontiers, not because they threaten understanding. Returning to the larger cosmic picture also encourages attention to the role that measurement and observation play in shaping theory. No singularity has ever been observed. No infinite curvature has been detected. All evidence points toward finite behavior. Even inside black holes where measurements are impossible, theoretical work strongly suggests that infinities do not occur in nature. They appear only in equations. The equations reveal their own limits. Reflecting on the history of ideas that led to these conclusions makes the path forward clearer. Einstein's equations were not built with quantum fluctuations in mind. They were built to explain curvature as a continuous structure. That structure matches the observable universe at most scales. Yet when the equations reach extreme environments, they begin producing values they were never designed to handle. This is not a failure. It is a guide. Gradually stepping back from this recognition allows the entire discussion to shift toward broader themes. Understanding the universe requires models that function across scales. When one model reaches its limits, extending the framework becomes necessary. The appearance of singularities provides the clearest sign that gravity and quantum mechanics must eventually be unified. Building that unification remains a long process, but the direction is established. The requirements are known. The evidence points consistently toward the need for a deeper theory. Letting the details settle brings attention to something else as well. The universe remains understandable even without full knowledge of its extremes. The regions where understanding ends are small compared to the vastness of cosmic space. They represent opportunities rather than obstacles. They encourage new ideas. They encourage careful examination. They inspire the search for a unified description. Returning gently from the dense mathematical argument surrounding singularities allows the larger conceptual landscape to appear again. Space expands. Matter forms structure. Stars are born and die. Galaxies interact. Light travels across billions of light years. These processes unfold according to well-tested rules. The unknown regions do not overshadow the known ones. They exist at the edges. They draw curiosity without undermining the stability of the broader picture. As attention shifts away from the intense gravitational scenarios described earlier, the pace of thought can slow. The complexities of collapse no longer demand immediate resolution. The unresolved nature of quantum gravity becomes less urgent. The singularity question, while still profound, becomes part of a larger continuum of inquiry. It no longer dominates the landscape. It becomes one thread among many. In this slower setting, it becomes easier to appreciate how stable the universe is at scales accessible to us. Systems evolve predictably. Orbiting bodies follow calculable paths. Waves of gravity travel cleanly through space. These features anchor understanding. They provide reassurance that even though the extremes remain challenging, the overall structure remains reliable. Gradually easing away from the frontier of singularity, physics also allows space for recognition of the simplicity that emerges when stepping back. The universe operates with remarkable consistency across vast scales. The need for new physics does not imply instability. It implies opportunity. It implies depth. It implies a continuing journey. Drifting carefully from the edges of collapse and curvature, the view becomes wider. The intense focus softens. The broader shape of physical law becomes more apparent. Patterns re-emerge, connections deepen. The missing pieces no longer feel like gaps. They feel like reminders that understanding is always expanding. The work continues. The models evolve. The universe remains steady as that evolution unfolds.